and respectful welcome to the 14th International Conference, Confluence 2024, Cloud Computing, Data Science and Engineering, organized by the Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for the empirical inquision. With this agenda, Conference 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. May I invite Dr. Nancy Gulati ma'am to present a virtual sampling to our esteemed speaker, Professor Dr. Chanchal K. Roy. It is our great privilege and honor to have amongst us Professor Dr. Chanchal K. Roy. Professor Dr. Chanchal K. Roy is co-director of the Software Research Lab and a professor of software engineering, computer science at the University of Saskatchewan, Canada. As the primary author of the widely used NICAD code clone detection system, he has published more than 150 referred publications, with many of them in the prior software engineering conferences and journals that have been cited more than 6,000 times. General Google Scholar profile, Dr. Roy works in the broad area of software engineering with particular emphasis on software clone detection and management, software evolution and maintenance, and recommender system and software engineering. He received the most influential paper awards both at SANER 2018 and at ICPC 2018. He extensively serves in conference organizations and conference program committees. Now I request Professor Dr. Chanchal K. Roy to kindly address the gatherings with his words of wisdom.
So should I start or okay, just a minute.
Yes, sir. Please begin
Yeah.
with proceedings.
Can you see my screen?
Yes, sir. It's visible.
Yeah, sounds good. Yes. Okay, so first of all, thank you, Dr. Gulati and Dr. Garima Agrawal for inviting me and for giving me this opportunity for talking about my research in this around conference. And I see there are a lot of speakers from around the world, and it's really a great pleasure talking here. It would have been nice that I would be there physically, but actually recently I got a surgery, so I was planning to go this year in person, but couldn't make it. I apologize for that. So my research is on, I do a lot of work on software maintenance, software engineering, data analytics, but here in today's talk, I'm going to mostly focus on software clone and software clone analysis, and why do we need it, or why you need to detect them, what are the issues, how do we benchmark them. In particular, what happens in this AI era where you can make a lot of clones automatically, let's say by, with ChatGPT, for example. So first, what is software clone? So I have 30 minutes, right? Or I have less right now because we are running late. How much time do I have?
Yes, sir, you can take your time, like 20 to 25 minutes will be fine. It's up to you.
Okay, yeah, thank you. Yeah. So software clone are nothing but two similar pieces of code where you can, like when developers copy and paste, for example, here you can see that because it is copy paste is common, like people will copy a code fragment, paste somewhere else, and then they might reuse it and they might modify it. Like sometimes they just, copy paste directly without any changes or maybe small changes. Sometimes they change the variable names, for example. Sometimes they can do further changes, like a lot of lines added, deleted, modified. A lot of things could happen, and sometimes there could be even semantic differences. Like something is in for loop, something could be in while loop, something is in recursion. Like but they are maybe doing the same thing, but there are no similarity between the code fragment. So there are different types of clones. Like see here, this one. One is using loop in Java, and another one in let's say for linear search in recursion. Or for example, if you look at this, the same thing, the palindrome program in 4 different, like if you look at this Java code, this is palindrome, and this is palindrome in Python using recursion. And this is also Python code for palindrome just using list slicing. So it's just one line. But then how do we think that they are similar? So this is one of the problems I'm going to talk, like how do you think they're doing the same thing, but if we compare them with like different kinds of tree or with token or with line or with graph, nothing will match because they're not really similar. So the question is, why do we really care? Are there really any clones? And the study shows that there are a lot of clones in the system. Sometimes it could be even 50%. Clones, again, the similar fragments of code in the software systems. And why there are so many clones? Copy paste is common practice. Developers often copy paste, and they do not want to do new code. Because there might be risk in developing new code. Some languages even do not, offer you procedural abstraction. So they have to, like HTML, for example. So they have to, copy paste and reuse, right? And on the other hand, for example, clones are not really good. If you look at Beck and Fowler's the bad smell book, like the string parade of bad smells, this is the #1 bad smells. So it's not good to have this in the system. And clones are also bad because it could propagate bugs. So sometimes bugs could cost trillions of dollars. And how does it propagate bugs? Let's say if you have a fragment that has a bug and you are copy pasting and reusing that fragment over and over again, that means you are propagating the bug. And it could also make code bloat in the system. On the other hand, again, a lot of people, or even including the industry, people are using copy paste as a kind of engineering tool because this is essential. You have to copy paste, and often it is intentional. I am copying it, pasting it, reusing it. I am changing it, adapting to the new context. I am doing it intentionally, right? And if I am doing it intentionally, if I am doing it correctly, maybe clones are not really harmful. Maybe clones could be good, right? So, and sometimes it might not be possible or practical to remove clones. You might have to keep it in the system. But the problem is there are some bad clones and some good clones, because some clones might really create problems in the maintenance. So if you have clones in the system and they have bugs, or if you are changing a clone fragment in the future, say you are changing one fragment, but you're not changing the other. So those fragments will create problem. There will be inconsistent changes in the system, and they might, lead the system to severe unexpected behavior. Consequently, the system might fail, right? So that's why the overall objective of this research, for example, is called clone management, and where we say, okay, well, we do safe cloning. And what does this safe cloning mean? The safe cloning means, okay, if somebody is copying and pasting a code fragment and they're using it by adapting, then provide a set of tools and techniques so that they can do this without any issues, without introducing new errors, new problems, new bugs, or without introducing inconsistent changes. Like if you because clones are similar fragments, of course. So if you are changing in one fragment, you should provide a tool support so that other fragments should be automatically changed, or at least, it will alarm you, okay, please change this one here too. And who are making that change, it should help you with different tools to do it consistently so that you do not introduce any further problem. So this is one of the things we call it safe cloning. And because when you do cloning, there are also risks, there are benefits, right? There are compensation that you might need to pay, like technical debt in future. You might need to remove them with refactoring, so clone removal. So that's the objective. And recently, actually, we with one of our collaborators, we have a lot of surveys in these areas. We also did in the past, but recently, just last year, we did one survey, just only on code similarity. It was a systematic survey, and we just tried to find out what are the definitions of similarity, what happens. And we use this systematic approach. I'm not going to go. Somebody interested, they can look. And we have different questions. And we found that, there are a lot of studies still just for on, different kinds of similarities. And in last year even, they're among the highest. And there are different kinds of similarity that could go. As you can see from this diagram, it could be, this code similarity measurement could happen in terms of different languages, different techniques, different applications, different tools, in terms of different data sets, static or dynamic. And then for each of them has, different kinds of other approaches in it. So this is kind of how vast this code similarity approach is. I'm not talking about measurement. I'm not talking about removal, not talking about any other tool support. I'm only talking about what kind of similarities are there and how to detect them. So one of them is like this machine learning based, deep learning based. Sometimes you can compare the lines, sometimes you can compare tokens, compare graphs, compare the ASTs, abstraction entities. But then also you have different kinds of application for different types of clones. So it's a kind of a big kind of different kind of ugly mess for different applications. Like you can not only that you can detect clones for your software maintenance, but it could also for malware detection, plagiarism detection, defect detection, or sometimes you can do code recommendation. For example, right now, a lot of things are happening with machine learning, right? They're recommending code, they're generating code with generative AI, but it is a lot of insight. It is fast to learn the similarity between them and then to do all other thing, right? So that's the code similarity problem. So it's not only one clone. This is actually the fundamental problem for any software engineering tasks, or maybe right now, anything that we are doing with AI or anything, like everything is kind of sequence missing, pattern missing, similarity missing. So different kinds of techniques, different kinds of tools are used. And this is kind of a percentage we found recently for this survey, that what percentage of techniques are using what kind of methods. A lot of people are using hybrid method. Some are using learning based, like this is the it could be machine learning, deep learning, and that one. Different kinds of similarity measures people have been using. Like you can say, okay, how many lines? I mean, if you are using machine learning, for example, they have to find out this different kinds of features, right? So you can look at the code, you can look at what kind of properties we can look at. So there are different things. We look at the line of code, we could look at number of variables, we look at the for loops are being used, cyclomatic complexity, or blah, blah, blah. But, still, there are other approaches where, as I said, we can use graphs, or we can use tokens, we can use abstraction entities, a lot of different things we can use, or program dependency graphs, and then we can compare them, right? So again, a lot of tools are out there, as I said, by this survey, as we've also recently found. And I can see just list some of the tools here, hundreds of tools available. Actually, if you search with clone detection tools, there will be a lot of tools available. Yeah, this is kind of, again, the hybrid method is maybe the most people are using. Not only one method, not only comparing the tokens or comparing the different features, but maybe they're using another approach, like, okay, can I compare line and AST? Can I compare token and machine learning, and all those different kinds of representation in machine learning? Then what happens? Yeah, so also there are different kinds of languages that have been used in clone detection. We see that the Java is being the most in our recent survey. And also there are a lot of different systems. Projects are being used, and we can, a lot of common projects are being used in different studies. And we can see that DNS, Java, PostgreSQL, and a lot of different systems are being used too. The question is about these tools are classical tools mostly. And the question is, what about large scale clone detection? So because today's data is very large, right? So, and if we do not have enough hardware, so if I have just my laptop, can I detect clones from large scale clone? Like if I have thousands of projects, can I detect inter-project clones, right? And if the benefit of those large scale clone detection is that you can have license violation detection using clone detection technique, or you can build new libraries for, like if you can detect clones from thousands of systems, then maybe you might find a lot of similar things that might turn into libraries. Or like if you are developing software, you can, like for example, Copilot, right? You can essentially recommend different kinds of APIs by looking at the similar, or even code fragment when you are writing code, when you are doing the code completion. So all it needs is actually to do first step is to detect clones from large software systems or even code source, right? So we have done one of those tools. We call it CloneWorks. It was published in ICSI a few years back, and it was tested with 25,000 Java projects, about 250 million lines of code. And you can run it with actually a standard personal computer, and it can detect clones from 25,000 Java projects that has 250 million lines of code, in very fair amount of time, and like in only maybe 1 hour or less, something like this. And most often it is supposed to fail, but we did some approaches. We did different kinds of approaches so that we can deal with larger scale data, and also we did a lot of kind of customization. So you can remove the differences between the code fragment so that the detection capability increases significantly. Like when you copy paste and modify, there are a lot of differences happen. The idea is to minimize those differences and then apply the clone detection. So that's what we did. So people can look at it in it. Like again, come back to this example I was talking about at the beginning. Like if you have cross-language clones, like, or if you have, then maybe the CloneWorks may not even work, for example, because CloneWorks was only designed for single language clone detection. So if we, like this example was, it's like completely different. Like one code is just 2 lines. And how do you say that these 3 fragments are similar? And they are in development 3 different, like at least this is in Java and this is in Python, right? So what we did, we had this one tool that we published in ASE in 2019 about, it's called CLC DSA, where you use deep learning and different kinds of feature extraction. But what we mostly did was also is we tried to make it language independent, because we are going to compare one software like from a Java system with another system like Python or with C#. Then how can we do it? What is the bottom line? What are the things we can we really? Because if you look at just the features of the source code, this will not work. Like here in this example, if we look at the features of the source code for machine learning, they will not work, because it might not give us the right answer, because this one and this one particularly doesn't match. So what we did, we looked at mostly to look at the description of the method calls or the APIs. So if you have this print line, what does this print line mean? So we go to the library description. Similarly, if we have another language, it is called write line. So maybe we instead of looking at this code, we go to the library description of that. And then we look at those descriptions, and then we do some lot of along with some other features, we use deep learning to detect how these 2 fragments are similar. So this was that paper. So we call it API calls similarity measurement, and then we apply those different kinds of approaches and find out the weight and find out how we can detect clones from different languages. So it's not only single language clone detection. Now right now we can detect clones like if you have a lot of systems of different languages, we can use our tool, and then we can still say what are the similar. The usefulness of is that still you can maybe use it for program understanding. If you understand one system, maybe you can understand the other easily. If you want to look for the code reuse patterns, how developers reuse code from one language to another, you can study them. You can find out the clones in different languages, and you can study the patterns. right? You can also find out the toxic fragments between the languages. If you think that this kind of fragment is toxic in C systems, then maybe what are the similar fragments in Java that might be also toxic? So you can find out the toxic fragments. If you similarly for buggy fragments, for example, if you think that this kind of coding pattern introduces bugs in C systems, maybe they would be also introducing bugs in Java systems. So you look for the coding patterns and find out. There are a lot of different implications for this cross-language clone detection process. Then we have another cross-language clone detection approach, the cross-language clone detection approach, where we use transcoder. Transcoder means the transcoder is like we have this Meta or formerly Facebook, like you can convert C to Java, for example. So we use a single language clone detection tool to detect clones from cross language. So what do we do if we have a system in Java and another system in C? Then we will convert the system using transcoder to Java, and then we will detect the interproject clone detection for Java clone detection tool. So we also did it. So it's for transcoder. We also had to because we also use deep learning based approaches, so machine learning based approaches. We also did some learning, and then we also use. I will talk about mutation later. But mutation means you can artificially generate data. So given the original data, and then we also tested it with artificial data and augment the data set for learning. And then we kind of found kind of better result with artificial data as well. So we have to increase the data set for learning. So because we do not have enough data, so we wanted to increase the data set using mutation-based approach. And still the transcoder, along with the mutation, was giving us better performance while we was doing cross-language clone detection, for example. Look, this one's reading a file in Java and reading a file by Python code by transcoder for this. So now, they're different, but if you have something in the same as Python, because we are transforming using transcoder, then maybe you can get better performance when you're applying clone detection tool. So transcoder is we found it kind of useful for our purpose. But the main problem is one of those main problems for this. I think I am already kind of 18 minutes. Is about how good your tool is. What are the performance of your tools, because we do not know. The clone detection is a problem where you really do not know how good your tool is, because we do not have a good oracle. So if you had known that, okay, this system has this many clones and my tool has detected this many, then I could have confirmed that, okay, my tool is good or bad. But we really do not know what is the oracle. And making that oracle is also a big problem. So precision, like this is the problem with recall, because if you do not know the oracle, you cannot measure recall. Precision is sometimes you can do it, hand validating like some samples. So that's we can do. But the oracling problem is a big problem. So I'm not going to go in details about this definition right now. So I'm just saying that oracle, you need oracle for recall. You can hand validate your precision. And the problem being not having oracle is there is no good definition of clone. So there is no fundamental theoretical definition of what is a clone. How do we say how much changes you could make before it is not really a clone? Because you copy, paste, and you modify for the context. And if you ask people to validate clones for the same two fragments, different people will say different answer. They'll say, oh, they look like similar because of this. Some people say, oh, no, this is not clone. Some people say, okay, for my case, it doesn't look like clone. I don't really care. So sometimes it's actually use case specific. For your case, some people might say, okay, I'm only looking for the clones that is refactorable. So that person will only say, okay, this two fragment doesn't look like refactorable. Then say, okay, then this is not a clone. So it's a lot of huge debate on this. And there are a lot of issues we talked about in the past, and we found out. I'm not going to go in details, lack of time. So what we did, we tried to use one of those approaches using mutation theory. So mutation is very well known in testing community. We tried to use that approach by artificially generating thousands of clone fragments of different types using a meta model of clone types. So we model the developers copy paste behavior, and then we found out different kinds of modeling behavior, different kinds of copy paste activities. And based on those different kinds of copy paste activities, we take a fragment, and then we automatically generate different kinds of fragments. That is that could be a clone fragment of the original one. And then once we have thousands of those fragments, we can inject into the system, and then we can keep them in a database, and that database will have a lot of thousands of known clones that we generated using the mutation theory. And now that we know what are the clones, we can now, measure the tools performance in terms of recall. However, I should note that this data set is artificial data. Although we mimic the developer editing activities, they are not really real. They are artificial. So what we need a data set that is built with real data set. So for this purpose, we actually did another benchmark, which is called big clone bench. And this big clone bench we have created it with without any tools, so that there is no bias for the tool. We use normal grep search. So we use, let's say we are thinking about a functionality, then we did some sample functionality. And then for each of those keywords in that functionality, we search 25,000 Java projects, which has 250 million lines of code and 2 million source files. And then we use 9 judges. So like if you search, okay, what is the implementation for MD5 hashing? And then we pick a couple of keywords for MD5 hashing, and then we search in the data set, and then we find thousands of fragments, and then we hand validate, literally hand validate by different judges and cross-check. And then we found out different kinds of clones. So this is kind of widely used benchmark. You can search with big clone bench, and then you can see that a lot of people have been using it. This big clone bench benchmark, and that although we made it for like comparing and evaluating clone detection tool, a lot of people have been using it for deep learning, machine learning based process. So this is kind of how we did it. The approach I was talking about in short. I'm not going to go in details. There are a lot of clones in them, like 8.5 million true clones in that benchmark. And then we also have like kind of an web-based system where you can evaluate your own tool, just plug in your tool, and then you can, all other tools are already there. So you can validate your tools without big trouble. So you can just go to this, we have a website, that website, and people can go and test their tools. And also we have this big clone bench and this data set I was talking about. All are open source kind of thing. Everything we provide is open source. The problem with this big clone bench is that it doesn't really have enough semantic clones, and people have been using this for machine learning, which we don't like. And also it doesn't have enough good semantic clones. That's why you cannot even compare or evaluate the semantic clone detection tools, which is why we created another benchmark, which we call semantic clone bench. We use it using Stack Overflow. So we look for Stack Overflow, look for a question, and then we look for what are the different answers people provided, and then we hand validate it, and we build this. I'm just saying in short, but the problem is this benchmark doesn't have enough data set. We have it for 4 different languages, but it doesn't have enough data set for machine learning or deep learning or whatever you can say. And that's why recently we just published last year a benchmark. We made a benchmark which is we call GPT clone bench. So we made use of GPT-3, and then we look at we picked up a fragment from semantic clone bench, and then we give it to the GPT, and then we get a lot of different kinds of code fragment, and then we validate with again 9-10 judges, and we also did some unit testing, validating by other tools, and then finally we got in that. This is like, again, this is only targeting semantic clones, because we are targeting all other clones as false clones. We have this 37,000 true semantic clones, 20,000 cross-language clones, and 19,000 false semantic clones. So this GPT clone bench is now very well kind of ready for using any deep learning kind of a process to use to learn. Again, the problem is this is based on GPT. Although we use semantic clone bench as a vehicle to search GPT and then to find out it, right? So it is kind of an artificial in the middle of artificial clone and real clones. But then we looked at, okay, what are the difference between them, between real clone and GPT clone? We found that actually patterns of this artificial clone, real clone, or clone by the copilot, it mostly looking like the same. So it is not, we do not really know exactly whether there is any big difference with GPT bench, or if somebody made another benchmark that is realistic semantic clone bench. That would be very helpful if somebody can really make it. But I don't know how easy it is, or how time intensive it is. Yeah, so this is GPT clone bench. People can use it. It's already being, people have started using it for their machine learning. So as I noted, this is also available. Everything is open source. Dataset is open source. Our experimental results are also open source, where we also use different tools to test this benchmark. And as I said, we do different kinds of validation using functional testing, manual validation, validation using another tool, all those different things. We also have a validation tool where we use different kinds of machine learning approach, then we can further validate the clone fragments. So I'm not going to talk about in all those details because of the interest of the time. What I'm going to conclude soon is that we recently also looked at whether these deep learning-based models are any good for semantic clone detection. Because now with that, we have different benchmarks. I was talking about these 3-4 different benchmarks, including machine learning, semantic clone bands, big clone bands, GPT clone bands, and mutation-based benchmarks. So we have 4 types of different benchmarks. And because we also did this cross-language clone detection, we also have this CLC-DSA benchmark. So we have different semantic clone detection and other benchmarks. So we wanted to see whether the recent approaches, like recent deep learning-based approaches, are any good for semantic clone detection. So we use these different data sets, including single language and cross language, and we use these different kinds of machine learning, deep learning-based approaches like CodeBot, ASTNN, GMN. A lot of things are in the different papers, and also cross language tools. One is token-based C4, another is our own tool, CLC-DSA. And then we looked at, again, I said, we have, that means that because we are taking a lot of different kinds of data set, and this data set has a lot of different kinds of clone pairs. So this kind of oracle, right? We know that they are clones in this data set. So we can apply both for learning and testing using this data set. And what we found is that for those different kinds of models, that when you work with big clone bands, the models achieve a lot of, it's a good, the current deep learning based approaches achieve 90% sometimes in big clone bands. And in the semantic clone bands, it drops because it doesn't have enough data, maybe significant drop when it's scored. And but when you CodeBot is also it's getting very good. CodeBot is one of those token-based approaches for separating semantic clones, right? So what we found is that if you have a good data, and which maybe everybody is finding it, right? So data set largely impacts the performance of the models. So if you don't have a good data set, the model doesn't really matter, or whatever good model is, it is. The graph-based models are performing better. CodeBot also performs better, in particular for semantic clones. So again, this is my maybe summary talk. I mean, what I'm going to say is that despite decades of active research, like we have been doing a lot of research, a lot of other researchers have been doing a lot of research, but still the scope of this area, like, is, there is huge amount of work to do in this area, because you can even, still we do not know what is the right definition of code similarity. We do not know what are the maintenance implication of it. We do not know properly how do we deal with bugs in the clones. We do not know how can we, how can we deal with when the software system evolves? How can we smartly deal with the clones in the system? We do not know how do we have different kinds of, we provide support we provide for refactoring the clones. So it's a big, it's kind of a big kind of game. So if somebody is working in clone, they are kind of, you can think of like in this shaded area, like this dark area. This dark area is mostly solved. So this is kind of solved, but this one is still not really solved. But if you look at the outer bound, the lighter one, nothing is solved. So it's all those parameters. We have a big survey also outlining all those things. So these things are not really solved. So it is a game. If somebody is working with clones, they can find, and that's why maybe there are a lot of papers, a lot of people have been working. You can find a lot of issues. And now that we also have this deep learning, we have GPT, this also increases further avenues for more research work in this area. So thank you again. Thank you so much for the opportunity for this talk. And I'm now ready for questions.
If anyone has doubts, if anyone has doubts, no. Thank you, sir. With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the Amity University, Uttar Pradesh, thank you all the guests and dignitaries for their significant presence. We would also like to thank you to the students for their cooperation.
And I want to again thank you, Dr. Gorima Agrawal, Dr. So all the organizers and everyone in this conference. And one thing I would like to note that is in our group, we are looking for a lot of students. And so Professor Nancy Gulati might also let the students know that we are looking for MSc, PhD, postdocs, different kinds of students, not only in this area. We provide a lot of flexibility. So if somebody doesn't like this area, it doesn't matter, okay? So it's this is one part of my research. So again, thank you, Dr. Gulati. Thank you so much.
Okay, thank you so much for sharing your knowledge with us. Thank you so much, sir.
You're welcome. Thank you.
It's not here. Invite कर दो पहले वो okay firstly ना
Dr. Hisao, are you there? So we can start the session.
Yes, yes. I'm here. Yes, I'm ready.
A very good morning to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Yash Gupta, express a warm and respectful welcome to the 14th International Conference, Confluence 2024, Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for empirical inquisition. With this agenda, Conference 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. May I invite Dr. Nancy Gulati ma'am to present a virtual sapling to our esteemed guest, speaker, Professor Dr. Hisao Ishibuchi. It is a great privilege and honor to have amongst us Professor Dr. Hisao Ishibuchi. Professor Hisao received the BS and MS degrees from Kyoto universities in 1985 and 1987, respectively, and a PhD degree from Osaka Prefecture University in 1992. He is a chair professor at Southern University of Science and Technology, China. He was the IEEE Computational Intelligence Society Vice President for Technical Activities in 2010 to 2013 and the editor-in-chief of IEEE Computational Intelligence magazine in 2014 to 2019. He was also an IEEE CIS Administrative Committee member 2014 to 2019 and 2021 to 2023, and an IEEE CIS Distinguished Lecturer. Currently, he is General Chair of IEEE WCCI 2024 in Yokohama, Japan. He received an IEEE CIS Fuzzy Systems Pioneer Award in 2019, an Outstanding Paper Award from IEEE Trans on Evolutionary Computation in 2020, and IEEE CIS Enrico Spini Award in 2023. Now I request Professor Dr. Hisao Ishibuchi to kindly address the gathering with his words of wisdom. Sir, please.
Thank you. Just wait a moment. How can I share? Can you share my screen?
Yes, sir, we can see your screen.
Okay. Okay, I'd like to start my presentation. Thank you very much for inviting me to give a chance to give a presentation here. Today's talk is on multi-objective evolutionary computation. And
Sir, are you there? Professor Hisao, can you hear us? I think he's left. Yeah.
Hello? Hello?
Yes, ma'am.
Yeah, Professor Isao Ishibuchi is in the waiting room. Could you please allow him to
Yeah,
enter the... Yeah, thank you.
भाई सर उनकी तरफ से कुछ इंटरनेट एक्टिवेशन
Hello.
Yes, Lee?
Yes, please allow Professor Ishibuchi enter the Zoom meeting.
Sure,
He's
just
in the waiting room. Yes. Thank you.
waiting room.
Hello?
Yes, Professor, we can hear you.
Oh, okay, okay. Thank you very much.
Yeah, you can start.
Well, I'm very sorry for some technical problem.
Yeah, no issue, sir.
Can you see my screen?
Yes, sir, we can see your screen. You may begin.
Okay. Thank you very much.
Thank you.
So I'd like to quickly complete because of the delay. This is a conference of this year, Neural Network Conference, Fuzzy System Conference, and Evolutionary Competition Conference. This is in Japan, Yokohama. We will have about 2,000 attendees. And then one important issue is that you can choose your presentation mode from on-site oral presentation, on-site poster presentation, and online oral presentation. If you think that it's very difficult for you to come to Japan, you can choose online oral presentation. Then you can give a presentation through the internet. The deadline is end of this month. We still have another 10 days. So I hope that some of you will prepare and submit your paper. Then we have a lot of nice speakers, invited speakers for neural networks, for fuzzy system, and also for evolutionary computation. And the good thing is we also have online invite speakers. If you cannot attend the conference, but you can attend the online invited talk. Professor Hussein Abbas is the editor-in-chief of IEEE transaction on artificial intelligence. And Eric is a well-known young researcher in the field of natural language processing. So please consider to submit your paper to WCCI in Yokohama. And I'd like to move back to the main part, multi-objective optimization. For optimization programs, usually we try to optimize a single objective. So this is a single objective optimization program. However, in real world situation, we usually have a number of different objectives. So most programs are multi-objective program. However, usually we focus on a single objective. So we usually focus on single objective program, but in reality, most programs are multi-objective optimization program. Here, this slide shows the number of papers published in each year with multi-objective in the paper title. So the height of each bar shows the number of papers published in each year. You can see the stable growth in the last 20 years. Now we have more than 5,000 papers every year on multi-objective optimization. Why we have such a growing number of multi-objective papers? The reason is here. Almost all real world programs have multiple objectives. For example, most of you are working on the design of some intelligent system, classifier design, controller design, some design of approximators, or a robot, or car. Any design, any intelligent design system, your main objective is usually performance maximization. You want to maximize the performance. However, at the same time, you have some other objectives. For example, cost minimization, energy consumption minimization, complexity minimization. So even when you are working on single objective, performance optimization, performance maximization, you have some other problems. Recently, many researchers start to think about these other objectives. As a result, we have many multi-objective problems. Here, this is an example, multi-objective neural network architecture search. Neural network architecture search is a hot topic recently. The problem is to find the best structure of neural network. Usually, we want to minimize error minimization, performance maximization. However, if we want to minimize error, we need a huge neural network, like deep neural networks. For some application, it is okay. Simply, we want to minimize error. Performance maximization is enough. But in some other application, we cannot use huge structures. We want to minimize the complexity. So the other objective is complexity minimization. But if we want to minimize the complexity, neural network size becomes very small. Then error becomes large. That is, we have a trade-off curve here. We cannot find inside the trade-off curve. So our problem is to find the best structure on this trade-off curve, from very complex neural network to very simple neural network. We cannot have any neural network structure here, zero error and zero complexity. Very simple neural network has large error. And then if we want to minimize the error, neural network structure becomes large. So we have just trade-off surface. The trade-off relation is the main part of multi-objective optimization. Due to the trade-off relation, we need to consider multiple objectives, but we cannot optimize everything simultaneously here. Another example is feature selection. The problem is to find a subset of given features. In some application field, we have thousands of features. Then in the design of classifier, we need to find a subset. We have the same trade-off relation. The main goal is error minimization. We want to minimize error by selecting some features. Usually, we have better classifier by choosing many features. But in some applications, we need to decrease the number of features. So one objective is error minimization, but the other objective is minimization of the number of features. Again, we have here trade-offs, clear trade-off surface. By increasing the number of features, we can decrease the error. But we want to minimize the feature. Then by decreasing the number of features, the error will improve. So our problem is to find the best subset on this trade-off surface. We have a number of Pareto optimal subset. Here, we show a basic idea of evolutionary computation, application of evolutionary computation to multi-objective optimization. In evolutionary computation, we have a set of solutions, population. And then from randomly generated initial population, we can improve the quality of that population. That is a set of solutions. Set of solutions gradually improve. For example, this is a two-objective maximization problem. So from initial population, we can improve population towards this direction. After 20 generation update, after 50 generation update, we have gradually improved the population. Then finally, we have a number of solutions along this palette front. So the final result of evolutionary computation is these red points. Each point is a solution on the palette front. And the evolutionary computation is to try to find these red points. So the important thing is how to search for these red points. well-distributed solutions along the palette front. This is a basic idea of evolutionary computation for multi-objective optimization. And here I show 3 well-known algorithms, evolutionary multi-objective optimization algorithm, EMO algorithm. The most popular one is NSJ2. This algorithm was designed in India by Professor Kalyan Dev and 3 undergraduate students. And currently the number of citations is 53,000. Huge number of citations. One of the most highly cited paper in the computer science field. And this is a typical algorithm based on Pareto dominance relation. Another well-known algorithm is MOUAD. This is a decomposition-based algorithm. The number of citations is 8,000. And this is a special type of algorithm, SMS-MOA. This is based on indicator, hypervolume-based algorithm. The citation is 2,000. These 3 algorithms are well-known and represented from each category. Pareto dominance-based algorithm, decomposition-based algorithm, and indicator-based algorithm. And all of these algorithms, and also all of recently proposed algorithms based on elitist mechanism. Elitist means that a good solution can survive to the next generation. Here we have a current population. From the current population, we generate children. This is the basic idea of evolutionary computation. From current population, we create children. And next population is selected from current population and offspring population. Good solutions are selected from current population and offspring. Here we have a next population. And then after the many iterations of this generation update, we have final population. In the final population, some good solutions are from the previous populations. For example, this black point is from here, and this red point is from here. So good solutions can survive to the next population. This is the elitist mechanism. And this mechanism is used in almost all MO algorithms. This is a very good mechanism because we can choose some good solution from the offspring population. For example, here we show 6 solutions in the current population, and we have 6 children. Then after generation update, we can select these good 6 solutions for the next population. So we can improve the current population by selecting a small number of good solutions from the offspring. If we cannot generate new good solutions, for example, here we have 6 black points, they are current population, and we have 6 new red points, they are children. All children are not good. In this case, we simply choose the current population for the next generation. There is no problem. Then we try to find the good children in the next generation. In this manner, we can improve the population, and then finally we have a good population. This is the basic idea of evolutionary multi-objective optimization. And this mechanism is used in almost all recent evolutionary multi-objective optimization algorithms. However, this mechanism has a number of difficulties. Those difficulties can be used for future research. For the design of new algorithms, we can realize potential difficulties of the current elitist mechanism. One difficulty is here. In general, the final population is not the best subset of all the examined solutions. Here we have final population. Final population is selected from the previous population and previous children. So that this final population is the best subset of these 2 populations. So G100 is the final generation. So G100 is the best subset of the previous population and previous children. However, this final population is not the best subset of all of these solutions. This is one difficulties. This point can be improved in the future, and this is explained here. We intuitively think that the final population is a good solution. Here we show all the examined solutions. All the examined solutions are shown in this figure, and red points are final population. We usually assume that red points are good solution. However, in many cases, as shown in the right-hand side figure, some final population, some final solutions are dominated by other solutions. Other solutions are generated in previous generation and removed in previous generations. So good solutions are not always included in the final population. We usually think that we usually assume that the result is something like in the left-hand side figure. However, in real situations, in many cases, many solutions are dominated, and those solutions are included in final population. This is one big problem. This issue was examined by this paper in MO conference paper 4 years ago, 5 years ago. Yep. And then they examined the percentage of dominated solution, percentage of these bad solutions in the final population. This slide shows the percentage. For example, MOEAD, this is one of the well-known, frequently used algorithms. In MOEAD, in some cases, about 30% solutions in the final population are bad solutions, dominated solutions. In NSCA2, here for some programs, 10% solutions are bad solutions in the final population. So in many cases, final population includes some dominated solution. This is one big problem. And another problem is current population should be always a good solution set. This is not so easy to understand, but I'd like to explain. The current population should be always good solution set, so the evolution is shown by this figure. From initial population, we gradually improve the population. In the leftmost figure, we show a very ideal situation. After 50th generation, we have pink point, and after 10th generation, we have this yellow point. In the middle, also we show some ideal situation. After 50th generation, we have this pink point, and after 10th generation, we have this yellow point. So this type of evolution is assumed. However, if we use the rightmost figure pattern from initial population, we focus on one corner, then gradually move towards the other corner. In this case, the current population is not good. So our current framework cannot use this type of evolution. However, in some situations, this type of evolution is needed. Here we show the problem more clearly. In the current mechanism, current population should be good solution set. So here we show we assume that the red curve is palette front and gray region is examined region. After examining gray region, we have pink point. Pink point are good solution among examined regions. So current population is always something like this pink point. However, our goal is to find this red palette front. So we want to focus on the center part. So the good parent should be around the center part, like these blue points. However, in the current mechanism, we always need to have good solutions in the current population. So the current population is always pink point. We cannot focus on center region using blue parents. This is another problem. And then the last problem, the third problem is the number of solutions. We usually use a limited population size. So the final population size is also limited. For example, 200. So in the final population, we have only 200 solutions. That is the 200 solutions are our final result. However, for many objective problems, we need many solutions to approximate the Pareto front. In the case of two objective, trade-off surface is a curve. So it's maybe needed, maybe it's 100 solutions is enough to approximate this curve. In the case of three objectives, if you have three objectives, the trade-off surface is a plane surface. So we may need maybe 100, 200, that's enough. However, in the case of four objective, Pareto front is 3D. So we may need more than 100, more than 200. In the case of 11 objective, Pareto front is 11-dimensional shape. If we assume the simplest shape, hypercube, 10 dimensional, 10 dimensional. In the case of 11 objective problem, the Pareto front is 10-dimensional shape. So if we think about the simplest shape, hypercube, and then let us consider the number of corners of 10-dimensional hypercube. It's very clear that we have 10,024 corners in 10-dimensional hypercube. So in order to approximate the 10-dimensional hypercube, we need at least 1,024 corners. However, in evolutionary computation, we can obtain only 200 or 300 solutions. This is a big problem. So in order to handle this difficulty, our idea is to use unbounded external archive. That is, all the examined solutions are stored here. All examined solutions are simply stored here. Then, after the termination of the algorithm, final solution set is selected from all the examined solutions, not the final population. Final population is simply the final population. We can select the best solution set from all the examined solutions stored here. Using this mechanism, we can solve many difficulties in the current framework of evolutionary multi-objective optimization algorithm. So by selecting good solutions, we can select only non-dominated solutions, as shown in the left-hand side figure. We can select good solutions, even when final population includes these bad solutions. This is a good point of using archive. So by selecting good solutions from all the examined solutions, we can obtain good final solution set. I'd like to show some examples. Here, this is a final population by NSGA2. Final population is not very well distributed. This is a final population. Final population distribution is not very good. But by using our mechanism, selection from all the examined solutions, we can obtain good distribution. We did not change any mechanism of NSGA2. Simply compare between final population and selected solutions. By simply storing all the examined solutions and use some subset selection mechanism, we can clearly improve the final population. This is the NSGA2 result, and this is the MOEA result. In the MOED case, the distribution is not uniform. Some solutions are stored, some solutions are concentrated on this region, and no solutions around the corner. So heavily biased distribution. But after using our solution selection mechanism, we can obtain well-distributed solutions. and also SMS MOR result. Final population is not well distributed, but using our mechanism, storing all the exam solution and select well distributed solution, we can clearly improve the final population. Also, we can use some good parents. Here, we show the current population and offspring population. Usually, we need to select well-distributed solution for the next population in the current mechanism. But in a new framework, we can focus on this part, not well search region. We can focus this part and focus our search effort on this region in order to efficiently find good solutions. So in this manner, using new framework, we can focus on some difficult part. We can focus some difficult part. In the current mechanism, we need to store, we need to have good solutions in the current population. But in the new framework, we can focus on difficult region. This is the advantage of new framework. Also, since we store all the exam solutions, we can select an arbitrary number of solutions. In standard framework, the final result is the final population. So the number of solutions is the same as the population size. However, in the proposed framework, we can select an arbitrary number of solutions. So if you need 10,000 solutions, we can select 10,000 solutions. If we need only 10 solutions, we can select those 10 solutions. So the flexibility is much higher than the standard final population-based algorithm. This is another advantage of the proposed new mechanism. And by using this mechanism, we can clearly improve the final population, as shown in this figure. The distribution is clearly better. And in this framework, we have a lot of interesting research topic. How to utilize stored solutions to generate new solutions. Also, how to utilize the stored solution to choose next population. And how to choose the final solution set from the stored solution. These 3 points are very interesting, and we have a lot of interesting research topics in this new framework. I think that I need to stop here because we are heavily delayed behind the schedule. So now I'd like to conclude my presentation. So my conclusion is only one sentence. We still have a number of interesting research topics in the field of evolutionary multi-objective optimization. As shown in this figure, this field is increasing every year. That's all for today. Thank you very much. And very sorry for some technical troubles in the internet connection.
Thank you, sir. Thank you for sharing your knowledge with us. Does anyone have any questions here? I guess they don't have any questions right now. Thank you so much, sir. With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the fraternity of Amity University, Uttar Pradesh, thank all the guests and dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank you, everyone. Thank you, sir.
Thank you very much.
Competitive advantage. Competitive advantage.
A very good afternoon to all the distinguished dignitaries and respected professors, ladies and gentlemen. At the outset, I, Anand Singh, express a warm and respectful welcome to the 14th International Conference, Confluence 2024 Cloud Computing, Data Science and Engineering, organized by the Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity is dedicated towards its responsibility of imparting its students with strong foundations and a platform for the empirical inquisition. With this agenda, the Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results and new directions in the field of next generation technologies. Now, may I invite Dr. Neha Agarwal to present a sapling to our esteemed speakers, Dr. Dinesh Manocha and Dr. Sharat Chandra Guntuku. Thank you. It is our great privilege and honor to have Dr. Dinesh Manocha with us. Dr. Dinesh Manocha is a distinguished university professor at the University of Maryland and Paul Chrisman Iribe Professor of Computer Science and Electrical and Computer Engineering. He is also the Phi Delta Theta Matthew Mason Distinguished Professor Emeritus of Computer Science at Chapel Hill University of North Carolina. Dr. Manocha's research focuses on AI, robotics, computer graphics, and augmented or virtual reality, and scientific computing, and has published more than 730 papers with the H index of 135. He has supervised 46 PhD dissertations, and his group has won 21 Best Paper Awards at leading conferences. His group has developed many widely and used software systems with 500,000 plus downloads and licensed them to more than 60 commercial vendors. He is an inventor of 16 patents, several of which have been licensed to industry, a fellow of AAAI, AAAS, ACM, and IEEE and Sloan Foundation. Dr. Manocha is a ACM SIGGRAPH Academy class member and a Bizer Award recipient from Solid Modeling Association. He received the Distinguished Alumni Award from IIT Delhi and Distinguished Career in a Computer Science Award from Washington Academy of Sciences. He was also the co-founder of Impulsonic, a developer of physics-based audio simulation technologies, which Valve Incorporated acquired in November 2016. He is also a co-founder of Inception Robotics Incorporation. Now I would like to request Dr. Dinesh Manocha to kindly address the gathering with his words of wisdom. Please, sir.
Thank you very much for your kind introduction, and it's an honor to be here. I'm enjoying your beautiful campus on a nice sunny Indian afternoon. So my research is on robotics, and I'm sure nowadays you hear about robots every day in the media, right? Robots are coming to your life. And the term robot is actually a very broad term, and I'll give you more context of that. The robotic itself is a pretty big field, so I'll especially focus within robotics on navigation problem, which is one of the core problems. So I have a large group at University of Maryland. I always claim you'll see a lot of PhD students here. I always give credit to my PhD students, on this work. I also work with Amazon, who's building a robot called Astro. I don't know if it's come out in India yet, but they're going to come with a home release robot. It's getting really popular there. But before I jump into my own work, let's see where we are. Robotics is not a new area. It's been around. The first robots were deployed in industry way back in 1960s. Probably none of you were born that time, right? And they were used a lot in industry for assembly, painting, tasks, medical robotics, surgical, and consumer robots come up. So, but this is, everybody talks about AI and other kind of technologies. This is the time we're seeing robots in all kind of shape. This is the medical robots here. They're very deployed for surgery. A lot of people are investing in humanoid robots, including Tesla, from Elon Musk. We soon have a human-like looking robots. These are big, but you also have small robot. This is Boston Dynamics Spot. Boston Dynamics now owned by Hyundai in Korea. This is like a small bug, a robot of the size of a fly, right? Just imagine a fly, autonomous fly, and snake robots. So in the last 10, 15 years, a lot of penetration robots have gone to warehouses. Most of you probably shop at Amazon, right? Or some kind of equivalent of Amazon. In fact, right now, there's a big company in Noida called Adverb, which is building big robot, one of the biggest robots for warehouses. So this is an example how robots are used in warehouses.
Advantage. Since rolling out the Kiva robot across its fulfillment centers, by 2018 they had 100,000 of them. By now that figure has comfortably surpassed 200,000. Amazon Robotics has been refining the design still further. The new iteration of Kiva, known as Pegasus, is 10 centimeters shorter, meaning more can be stocked on top and uses half the parts, so it's cheaper to manufacture and maintain. Amazon says Pegasus can lift a hefty 600.
So all the e-commerce shopping places, they have a big storage house. In US, some of them are 1 mile long, like 1.5 kilometers long, where they're moving stuff around. So that's a very big thing. And this another company, Berkshire Grey, they're using robots for a lot of e-commerce is getting a big
advantage. Since rolling out the
advantage.
Since
While warehouse is a very big success story, but the warehouse are designed to be robot friendly, where robots can work. The question is, can robots work in your campus? So you walk around the campus, you got ground, you got maybe mud, rains, you got sidewalks, pavements, or you got all kind of buildings. Other places where robots are very widely used are called vacuum cleaners. At least in US, Roombas are very widely used, but that's home. So there's a lot of excitement coming up here. So the navigation is a problem of making a robot go from location A to location B. It's like the basic task. It's almost like, you all use Google Maps, right? Google Maps tell you directions to go to any location. So same thing happens there. How do you perform same computation? So the work we're doing is, can we develop robot technology which can make them navigate anywhere, anytime? Like humans can walk, right? You can go anywhere on terrain. If it's not too uphill or not too dangerous, human can walk. But the robots today are very constrained. They live in live, good constrained place like warehouses. They're not very general. So what we are doing here is showing our work on robot
advantage. Since rolling out the Kiva robot across its fulfillment centers by
Okay, this is like here. So let me show you this robot introduced by Amazon more than 2 years ago is being selling for home robot called Astro. This is what this one looks like. See how robots are coming into your home.
A robot.
Yes.
What are we going to do with a robot?
Well, Astro, follow me.
Hi, Grandma. I miss you.
I miss you too. Hey, you got the toy I sent.
Yeah, I love it. Astro, follow me.
Cool. All right, race ya.
Come on.
Told you I turned it off.
And now I totally believe you. Ooh, yikes.
Message from Steve. Remember to eat something green today, Dad.
Check.
The robot which came in your
Thought we weren't home, huh? You thought wrong. It's a good try, though.
So this is an example of a robot they want to sell in your home. The question is, what can you do with it? So the challenge here comes out with the fact that everybody home is different. Everybody room setup is different. Everybody makes different kind of a mess. So one of the challenge Amazon is facing is in US, they're selling this robot for about $1,500, which is like what, 1,20,000 rupees. It's not a lot of money, at least in US. How can you put all the technology in the robot so it can work in anybody else's home? And there are serious privacy issue also because they cannot take your home pictures and send to the cloud. You know, everybody have their privacy. So could a robot be coexisting with you in your home? And there are a lot of challenges there, you know, because some people don't like it, the privacy is here. But the problem we are working with Amazon is they want us to develop a navigation system so it can work with a mess in your home. You know, you put stuff on the floor, your shoes are there, cables are there. Just like you walk around it, can the robot walk around it? That's a big challenge here. So this is the kind of situation comes up your home, you have constrained spaces, but home, the lighting conditions, they change a lot. So you may have a lot of glass around the home. You may have shiny floors. Humans can adapt to them, but the robots have something called computer visual sensors, which become very hard to adapt. So the goal here is to develop robot technology which can work in everybody's home. Now, it's not only that, before that, Amazon tried shipping orders by delivery, but by a not robot. The thing is, they were testing high speeds like this, which is easy. The question comes up, so this is, I have a student who works in Hong Kong. Think of robot market. So I always give an example. How many of you travel by Delhi Metro at 9 a.m. in the morning? How crowded is it? Okay. So here's a challenge for all of you. Can you design a robot that can walk around at 9 a.m. Delhi morning traffic as you can? Like how crowded it is, how you push around. I'm not asking you to be aggressive. So the question comes out to be is that 60% of the world population lives in crowded areas like Delhi, Mumbai, or Asian cities, right? Can the robots operate in such crowded environments? It's a big challenge for us, just like homes. So this is, you see on the left, it can do, cannot do. And when we talk about robot, the biggest money right now has gone in what is called autonomous driving. In US, you can buy a Tesla, which has some autonomous driving features, not safe. They test in US, this is like in California. You got very nice roads, well marked, pavement, and not much traffic. So you see, you might hear about Elon Musk testing at Teslas, Google way more testing in San Francisco, Cruise thing. But again, this is a nice street, and here's a footage which we actually got at city in China. One of my students got it. You look at it like this. Now we always joke the most challenging place to drive is actually Indian traffic. You got too many people, too many vehicles. So the question is, can autonomous driving car operate in these conditions? So you saw homes, you got crowded station, and you got traffic. So this is a good example of when can autonomous car come to India? That's a very big question. A lot of companies are struggling with that problem. So what I want to tell you about some of the work we're doing to solve these problems, robots who work in your home, in crowded station, or this thing. So the basic three parts of a robotic system is perception, mostly sensors like based on cameras or LiDARs. Planning, like if that's what human system works, you see the world around you, you see from your eyes, hear from your ears, the signals go to your brain make a decision, and the brain asks different joints to move, your hands, your feet, your body. So same thing we do, perception, planning, control. You perceive the world, make a decision, and take an action. And all this has to happen in like a 1/30th of a second so that you can react to a situation. So this is a challenge that robotics brings up here. So what I will show you in the remaining time, some of the work our group has done to deal with these challenges, developing autonomous robots so they can operate in different situations. So let's look at indoor scenes, right? So this is like a robot we put together. This is like a turtle bot. It's a cheaper robot. We put some sensors around it. You see a LiDAR. LiDAR is like a point cloud sensor. And then you got cameras. And then you see a laptop. We put a laptop here because a lot of AI that we're using called perception or machine learning needs GPUs, graphic processors. So this laptop is like the computation engine we integrate together. So our goal was that how can this sensor perceive the world, especially a lot of crowd, it's not as crowded as Delhi Metro, but it's crowd, and make a decision for robot to move around automatically. That's a challenge here. So again, I don't want to get technical details of that, but if somebody wants to know, those of you who learn about AI courses or simulation, to build a system like this, a lot of technologies come in the picture. There's something called reinforcement learning. It's a kind of AI, deep reinforcement learning. If you learn in a machine learning class, you learn about computer vision, you learn about projection, but we also do simulation. If some of you play games, like the game engines like Unreal or this thing, you train with them. So a lot of different technologies have come together to build a system like this. So this is, you can see my robot is about 2.5 feet high. It doesn't see full human. It's looking at humans walking, and it navigates between them. So this is how the system works. You got sensors, camera, LiDARs, go velocity. This is the policy, what we call basically AI term, the decision making. And this is how the robot moves in a collision-free scheme. And you want to make sure trajectories are good. So this is a couple of old video in our building when it gets quite crowded. So you'll see, you come and put the robot loose. So I was just standing in the video lobby of F2 building, a lot of people coming. Can the robot move around people? So this is our building. It's reasonably crowded, but you see some people act mean, right? They even put foot, but robot needs to deal with that. So this is where a lot of challenges occur. I'm having a little bit of a internet problem or a connection. Let me play the video again. So again, you can see how the robot is moving in like a dense crowd, especially like all the buildings you have. So you can build a robot, test it in your lobbies or different buildings you have, or go to the outdoor campus. So the thing is, this is totally unstructured environment for robot. It's moving in a crowded campus, and you see how people behave, especially when humans see robots, they act very differently, and the robot should deal with it. So you can see here again, somebody come in the front, robot needs to operate just like humans do. So this is the kind of a navigation we are testing in a crowded scenes. We can do it. And someday, as I said, maybe we can try it in Delhi metro station, because that's one of the most crowded environment. You see high density, how to deal with it. So there are more technologies here, how things behind the scene. We do computer vision. So right now, look, every human, it tracks in real time. It's looking at how humans are moving, put a bounding box for each human, and then predict how they're moving around. That's what really happens there. You see this here? So this is all dense tracking, because pedestrian, not only you track, but you also predict where they're going next. So this is the simulation part, which is called in machine learning simulation real. And we train on simulation environments, come here. So these are, some situation. You also come like this. So here, some people are just being mean, What if somebody comes and just stand in front of the robot? Just being very difficult, right? So we're testing here. Eventually, robot figures out and goes around it. So this is a kind of a situation where robots are dealing with it. And again, it comes here, you see it goes around that. So these are different kind of situation we're dealing with here. And even like narrow corridors. Suppose you go from a door, there's somebody to your left, you don't see it. And suddenly robot has to deal with it. So we're trying to make a system which can work with very difficult situations and robustly find the goal around it. That's how this goes. So this is towards indoor scene. Now, one challenge we faced indoor was glass. Our building at Maryland is one of the beautiful glass buildings. When you see glass, the computer vision sensors based on cameras don't work well. So we had to develop a good solution just to deal with the glass problem. So these are on the right too, you see some previous solution which failed during glass. This is actually my office with all window office. And you see very shiny floor, and the robot can navigate. So this was a big problem in the field. How do we deal with dense situations, so glassy situation? And again, transparent objects, because in home, you could have mirrors, you could have glass, you could have reflections, all kind of situations, and you go and deal with them. That's what really happens here. So this is indoor. What happens if you go outdoor? So outdoors are not so crowded as indoor. Of course, you can have political rallies, but outdoor different challenges. In indoor, your robot is on a floor, on a clear floor, like a dense floor here. It's flat. Outdoor is not flat. You could have hill, evens, or you could have terrains. We call it uneven, like very rough surface. It's not flat. How do we go with that? So this is our campus. It is very hilly. Now, this is a small robot. Sometimes the robot is so steep, robot cannot go up. So it looks into that situation. So we train with the situation simulation and go back and use them in real world here. So this is a system we have put together. You can see our campus is up hilly built terrain. So the previous method sometimes go wrong way and get stuck. So our robot on the left, look at the terrain, look at the sensors camera, figuring out what path it can traverse. Sometimes you can go uphill this way, you cannot go uphill this way. Suppose you go mountain hiking, the same decision you make. So this is a decision we're making with robots. We're going around different parts of the terrain and doing navigation in real time. So this is all in real time, and this is not a smooth surface, but robot figures out how to go up. That's where the challenge of navigation comes up here. You see more situation like this. Now this was still at empty ground. What happened? There are plants, there are bushes, there are shrubs, there are trees. How do you know which grass is soft you can go through and which plant is hard you cannot go through? So we have to do all this kind of situation. Humans are very good at it. For human it's trivial, for animals trivial, but for robots, this is a hard problem. So this is again a lot of work we're doing, especially in last few years. First of all, wheel robot, but you see Boston Dynamics, they show legged robots, right? Which is like just human. This has been the highest platform last few years. So this is one of our systems we built, which will show how we're dealing with very difficult terrain. You got like bumpiness, you got tall grass, you got bushes, you got stiff vegetation. how do you deal with all kinds of situations? So this was a very challenging problem in the field, and we're going around with that here. So you'll see different situations, how our learning and all planning, perception, control come together. This is the map, but let me show you a different situation. So this is what is happening inside the robot. The sensor sees the ground and do some ground analysis. So this is like here, the previous method can get wrong way stuck. Like if you make a wrong turn, you're going to bush, it's too bad. We automatically figure out what is a good way the robot can go through the vegetation. So this is all done automatically, just like humans do. This is a small robot. It doesn't get stuck or it doesn't take roundabout. It finds the shortest path automatically in this situation. That's number one. Now this is sandy. Sometimes it's too sandy, like it's very rough. Robot can figure out which ground surface is smooth or smooth enough to navigate and which are not so smooth here. Now this is the spot robot. You can see the Boston Dynamics, it's more dexterous. It can go through rocks, but sometimes it can get stuck in the vegetation. So we have to ourselves make a decision, just like human, what bushes you can go through and what you cannot go through. You see these kind of situations are coming here. So this is the kind of thing we are doing here. This is an example of something we showed, very tall grass, right? So this is a grass which is like 5 feet high, but it's soft. Some of it's soft, some is not soft. And the robot is automatically making a decision what grass is traversable, what is not. So this is again, these are not friendly places to walk. Robots can walk in open spaces, but robots could not walk. But this time we're doing automatically figuring out which robot space can go or not go. So this is an example, but Boston Dynamics come, if you take a solution, it doesn't make a good decision, it'll get stuck in a bad grass and fall over. But our solution on the left stops here and figure out, no, this is too difficult, I should not go. Sometimes you make a good decision, I should not go there. So this is there. My last part, I want to show you one other place where robots are getting a lot of places like safe construction. You go around Delhi, right? You see so many metro builds, so many excavation, they're human driven. What if we make construction equipment automatic? Now, probably in India, there's a lot of labor available, but in the Western world, there's a serious labor shortage right now. You want to put buildings, can robot do your buildings? Can robot dig your holes? Can robot do your mining? So there's other places where automation is coming. So this will show you excavators. You see how they're digging something and going around. Now this itself is about more than $45 billion industry worldwide. It's a huge construction business, like trillions of dollars. So can you automate construction? Now remember, construction happens 24 hours, day and night. It could be rainy day. It could be bad visibility. It could be sunny. Construction has to go on. So we want to develop robots that can work here. So this was the excavator we did. We put all the sensors. Any robot deal with sensors. You put cameras, you put real-time sensor, pressure sensor, inclination sensors. They all come together. We want to build an excavator which is totally automatic with computers and everything. So here's an example. There's a company in US, Caterpillar. On the left, there's a human operator doing this. It opens up and moves the sand. On the right, this is purely computer control, robotic automation. So left is human operated, like any equipment. On the right is automatic. And we're getting about 90% efficiency, figuring out how to fill, where to fill up, where to lift it up and go up. That's why it's going up like this. So as I said, when you do construction sites are not friendly. You could have a dry soil, you could have a wet soil, you could have rainy weather, you could have big rocks, you could have wet soil with mixture. All kind of situations come up and the robot system needs to deal with them. So that's the challenge here. So I just show you example. This is something we showed at Las Vegas. You see the robot is operating, totally automatic doing sanding, but guess what? And there is no human. So this was the world's first excavation system. This is the kind of situation we can deal with. So you can see we're entering an era, pretty soon construction, which is expensive, time consuming. Let robot do your construction. So you make a lot of buildings, can robots do the building? So this is the kind of situation we're dealing with. So here's robot operating, it works. Now somebody said, can you really operate? This is actually being used in mining industry and construction. So this is the example of toxic. So suppose you're dealing with very toxic material, which is not safe for humans. It can get sick. Let robot deal with it. So you see here the robot, there's no human operator. This is a view. is automatically figuring out and doing all your digging. So this is a big chunk of robotic application, and you see how things work here. And to show it works well, it's not just one time. This is used for 24 hours. So it's a camera showing 12 o'clock at night, 6 o'clock in the morning, 12 o'clock in the noon, 6 o'clock in the evening. 24 hours, it can work. And you can see when you start digging from bottom top left to bottom right, how it works well. So this is the kind of situation I'm showing you where we can take these technologies together and develop robust system. So this is where the future is coming. Robot in construction, robot for security guards, generate humans, robots who move your stuff from crowded situations. This is where coming up. Of course, this has come way, but still, because we are researchers, this is not a solved problem. One thing they were predicting in US, Elon Musk made a statement, we'll have autonomous cars by 2018, 2019. This is 2024. We still do not have faith in autonomous cars. These companies have spent $60 billion. Cruise had a big accident, they cut it off. So one challenge is that while autonomy is important, building fully autonomous systems is still a hard problem because there's so many special cases come up where things fail. So especially we're doing perception planning control, how do we do it? So autonomy is great to do, but sometimes people do overhype it. Oh, AI is going to take over your life. No, that is not happening because there's still challenging problems to solve. We're not there yet. So this is again to really show you where we are today, especially in the last 20 years. A lot of sensing, a lot of AI technologies have come together. It has a huge impact in robots. We can develop some good solutions for indoor and outdoor scenes, and we are showing good progress. But yet, there are a lot of situations, a lot of scenarios where we have open challenges. So for those of you who want to research in that, it's a great field because when robots come into your life, daily life, whether construction, home, shipping, it's going to change everybody's life. Are we ready for it? So I'll just stop here. Thank all my sponsors. Thank you for your time. And if anybody has questions or feedback, I don't know if you have time for questions, I'll welcome that. Thank you very much again. You have time for questions? Okay, you can ask if anybody has questions. You can ask.
If anyone has any questions, please present them to sir.
No questions? I don't think. Can I ask a question? Yes, please do. Sure.
Are there instances where you think robots should not replace human operators?
So I don't think of this human and robot replacing human because that's like personalized thing. I look at thing, can robots do tasks which human can do? So, there's something called, sensitive touch, right? Let's say you lift a small baby, right? I'm not going to have a robot handle your small baby, right? Now, people are looking into, for example, in some countries like Japan and Korea, humans are living longer, right? They don't have they don't have young people. So can robot be your friendly, personalized companion? Because there's a lot more goes to emotion, your sensitivity, and these robots are not the most friendly looking. So, I think humans are humans. So I don't look at it's robot versus human job. Humans will always be the more smarter species, and humans are evolution of billions of years. But I look at this way, like, transportation. In your home, robot can be a companion. In outdoor scenes, shipping, and you saw the excavation, toxic material, which is unsafe for human, mining. So I think of those are places where robots can have a huge impact. Any more questions or feedback? Okay. Thank you. So we can go for the next talk, and I don't want to change any cable. Don't worry about it. So
Thank you, sir, for the great session. Now I'd like to invite Dr. Sachin Manocha to present a memento to our esteemed speaker as a token of gratitude. Please, sir. So, we have another great session today. It is our great privilege and honor to have him with us. Dr. Professor Sharat Chandra Guntuku is Assistant Professor in the Research Track in the Department of Computer and Information Science. So, you want to connect with it? So, we'll just connect with Zoom if you want. Okay, so at the University of Pennsylvania, he directs the Computational Social Listening Lab. His research focuses on building predictive models for and uncovering insight into health outcomes and psychological states of individuals and communities. The goal of this research is to supplement clinical diagnosis and facilitate early and personalized interventions for improving treatments and well-being. He develops computational models utilizing large-scale user-generated text, image, and mobile sensor data to answer questions pertaining to geospatial, cross-cultural, and temporal aspects of human behavior. His recent work investigates the manifestation of conditions such as loneliness, ADHD, stress, and depression on social media platforms, and the role of heterogeneity in the digital behaviors of individuals across cultures. Now I request Dr. Sharat Chandra Guntuku to kindly address the gathering with his words of wisdom. Please, sir.
Yeah, it's already. No, that's not. That's a better. It doesn't matter. But okay. Sorry. Super. Awesome. Thank you for that kind introduction. And it's always a little challenging to go after a robotics talk because I don't have the cool animations and cool videos. But I'd like to talk a little bit about the work we're doing in digital mental health today. So specifically, we will discuss some of the work that my lab does on using language and images to understand people's health. We also work on multimodal machine learning for electronic health records, but I'll not be getting into that today. But if anybody has interest in that area, I'm happy to take questions. So let's first define what social listening is, right? So for example, there's a company, they have a product, and they want to sell it to a target audience, right? So they bring in a bunch of people and then ask them a bunch of questions and then try and understand who likes what, right? So for example, in 1920s, Chrysler was predominantly selling their cars to men, but then they realized that this particular automobile was more preferred by women, and then they targeted women in their ad campaigns, and the sales of this automobile sort of skyrocketed. Right. So similarly, I think many of you might be might be knowing about this. Spotify created playlists for different moods because often we do subscribe to different artists and different albums, but we do want, based on the mood, recommend me a bunch of different songs, right? So all of this is sort of a product of what people are telling them when you ask them a few different questions. But what happened after the advent of social media, right? So anybody and everybody who has internet access can basically go online and express their opinions free of cost without even asking any questions, right? So a lot of my collaborators think of social media as focus groups, but on steroids. So essentially, these are very, very active focus groups. So, and we also tend to spend a lot of time on social media, right? So in case folks want to take a guess, a 16 to 24, how many hours do you think we are spending on social media? Anybody? Okay, I think that's a more reliable estimate because this survey was done a couple of years back. It said about 3 hours. So that's a lot of our time, right? So that's an incredibly lot amount of time. And if you compare it with the amount of time or the number of times we see a doctor or a clinician, it's maybe what, 4 times a year, 5 times a year, right? So there's a lot of data that you're generating online that can potentially inform your health or how your treatment can potentially proceed. So that's basically one of our research agendas, to essentially check or to essentially build translational AI for social good with the idea of having real world impact in clinical informatics. And each of these have a couple of different challenges. For example, the first big challenge is social media is mostly used to show off your better side of life. Can it still be a reliable proxy for your mental health, right? It's unclear. And it's also costly to sort of get data from social media, right? So can you scale it to measure health of communities and not just individuals? So that's one that I'll talk about. And secondly, different people use social media differently. They talk about their mental health differently, right? So there's a lot of heterogeneity. Can you sort of use AI to sort of uncover that heterogeneity, right? So I'll briefly touch upon those two challenges. So this is the overarching question again. How can mental health be measured unobtrusively at scale using AI? But one could ask, why do I want to measure mental health? Is it really important? A lot of my uncles and aunts have just said, don't be lazy, just snap out of it. Depression is not real, right? So is it a non-problem that we are trying to solve, right? Let me try and convince you that it is an actual problem that we're trying to solve. Let's take the example of loneliness. Loneliness is essentially a condition where we are not physically, so there are two things. One is social isolation, the other is loneliness. Social isolation is when you're not with people, but loneliness is when you're with a lot of people and yet you feel alone, right? So it is sort of staggering that almost 30% of young adults, which is the age group that most of you fit into. If you look at 6 people, maybe two of them are feeling lonely according to this survey, right? So these numbers are sort of concerning. And loneliness has been linked with multiple adversarial outcomes. For example, there's a higher risk for depression, higher risk for dementia, higher risk for insomnia. And what is interesting, it also increases your risk for cardiovascular disease by 30%, right? So somebody is feeling alone, lonely consistently, their physical health gets impacted. And yet, not a lot of attention is given to mental health, right? Specifically loneliness. And there are studies that sort of compare this to being as bad as smoking 15 cigarettes a day, right? So it's incredibly bad for somebody to be feeling lonely consistently. So sure, it's important. Maybe you're convinced, right? But is it feasible to get it from social media? I saw a couple of folks saying, no, it's not feasible because it's mostly the positive side of things that people talk about in social media. So we've tried to look at getting this data in 4 different ways. One is you basically go to different people, ask them to share their social media feeds. It's usually a duration of 4 to 5 years of social media data. We also ask them to enter a bunch of surveys. So things like PHQ-9 or UCLA 10, which are essentially measuring how you're feeling. And that's what we call a self-reported survey data, right? So these are usually the gold standard in psychological studies. And then we've also looked at Twitter. For example, in US, a lot of people just go online and say that I am feeling lonely or I have been diagnosed with depression. This is not the case in other cultures, right? So for example, we also tried to look at something like this in China, and maybe among 400 million tweets, we found 6 mentions of people self-disclosing their diagnosis. And that's also partly because of stigma and whatnot, right? And then maybe a lot of you know Reddit. Reddit has multiple sub-communities called subreddits. You can sort of sign on to say depression subreddit or loneliness subreddit and so on. So forum membership is another way we can identify folks. I'll not get into post-level annotation, but essentially you can also look at different tweets and then annotate using expert guidance. So we had multiple studies published looking at expressions of loneliness just using language, using language and images, this one in AAA. And interestingly, you get a lot of signal, right? But at the same time, are these valid? Can you sort of validate them against ground truth? So we sort of trained machine learning models to take a bunch of text from people's social media feed, and we validate them in a trained test split in the same population, and we get a AUC of 0.76. If you took a typical machine learning course, and if you report an AUC of 0.76 in one of your problems, you're likely going to get shot, right? So this is a very, very bad performance metric to report. But at the same time, we should consider the task that we're looking at. This is not object recognition, right? This is not image classification. This is a much, much harder task. You're looking at somebody's social media posts and asking the question, is this person depressed? Is this person lonely? It's a much harder task, right? Then we also trained a model on self-disclosed data, which is the one that I was talking about on Twitter. We tested on the self-reported data, again, AUCs of 0.7. And what is sort of interesting is you train these models and then you apply them on other modalities, right? So let's say SMS or oral transcripts. They still generalize. So this is actually a study that one of our collaborators did, where they have audio recordings of survivors in the World Trade Center crash. And they applied the same models that we built on the audio transcripts of these survivors. And surprisingly, the models work really well, right? So they're generalizable, in other words. And the other gold standard in mental health, at least, is electronic health records. So whenever you go to a hospital, there's an electronic health record created. And we at Penn Medicine, we've collaborated with the School of Medicine to get both Facebook data and electronic health records from about 6,000 Penn Medicine patients. So this is now 4 years worth of Facebook data, 4 years worth of health records. And now you can basically ask the question, can I predict an incidence in health record before it actually appears, right? So can you sort of use just language on social media to predict if somebody was diagnosed with depression before they were diagnosed with depression, right? So we've had multiple papers on this, but essentially a summary is you can sort of predict depression almost 6 months before official diagnosis, right? So the signs are there. They just don't get recognized. We can also predict emergency room superutilization, right? So somebody is going to the ER more than 6 times a year. That means they're really sick. So you can sort of get that from people's language. And interestingly, these are all prediction accuracies, right? So AUC of 0.75, it's not a lot, but it's something good. But can you do something more than just predictive accuracies? Can you tell me what people are actually going through when they're feeling lonely? Can you sort of tell me what can I do if somebody else is feeling lonely, right? So can social media offer that insight, right? So this is a recent paper that one of our postdocs did, where we're trying to contrast loneliness and depression. Often mental health conditions are comorbid, right? So if somebody is depressed, they're also anxious, they're also lonely, but it's very difficult to sort of tease apart what comes first, what comes next. But teasing apart is helpful to basically create treatments. If you want to address loneliness, it'll be helpful to know what will actually treat loneliness. So this is the first order of results. Both loneliness and depression have a common language footprint, right? So the most prevalent being I talk. So I want, I don't, I'm not feeling well. It's a lot of self-referential talk. If somebody is having a lot of self-referential talk, that's a big marker for bad mental health. And if somebody is talking about, our, or, the collectivistic talk or social relationships, activities, these are often protective of bad mental health. But what is unique about, let's say, depression is if somebody goes to the ball game, if somebody goes to, let's say, social gatherings, even with strangers, it can sort of help somebody get out of depression. But for loneliness, that's not enough, right? So you need to have meaningful relationships. So there's a distinction here between social activities and social relationships. And one is more helpful for loneliness and the other is more helpful for depression. right? So similarly, you can see what is the risk factor. Again, similarly, I'll not get into it, but basically negative feelings and more cognitive and observational tasks are more of risk factors for us. Cool. So that sort of told us that we can validate some of these measures, right? But I also talked about having done this at scale. So can we sort of scale these measurements, right? So a lot of this, what I talked to you previously was with maybe 2,000, 3,000 people, but can we go from individuals to communities? So let's maybe rewind 3 years back. We don't really want to go there, but what happened was within a span of 1 month, people who were traveling 3 to 4 miles a day for commute basically got locked up in their own apartment, right? So this is a graphic from New York Times showing Seattle, and the average commute reduced from 3.8 miles to about 61 feet. And this had extremely negative mental health consequences beyond all other consequences. And this increase in mental health, or increase in mental health concerns, was unprecedented in the actual meaning of the term unprecedented, right? So Gallup is a nationally representative survey that they conduct on multiple Americans, and they found that over a span of the last 6 years, even though it's only showing till 2018, they've not seen these kinds of trend increases, right? So for example, percentage of people who were worried rose from about 38% to 60%, right? So it's about 20% increase in number of people who are feeling worried. So what could we do with all our models, right? So we have these individual level models that we built. We extract language features from people. We build these machine learning models, but we also have community level language from Twitter, right? So we can actually get random sample of Twitter and then geotag them to different, let's say, districts in India or counties in the US or boroughs in the UK. And we could basically apply the same models that we built on individuals to language from different communities. But at the same time, these are not the same, right? Because these are different domains. So you need to apply a little bit of domain adaptation. I'm not getting into the technical details of it, but after a couple of simple domain adaptation techniques, these models actually generalize pretty well, even to communities. So for example, these are all language predicted estimates, right? So the green line here shows data from 2019, and the orange line shows data from 2020. And you sort of see immediately after the national emergency declaration, the Z-scores of loneliness increasing by almost 2 standard deviations, which is very, very high. So we did something similar for depression, anxiety, stress, suicidal ideation, life satisfaction. Essentially, we have models that can predict these outcomes just by looking at somebody's words from their social media platforms. And we've also validated these against Gallup community level indices were available. And beyond that, we also actually put out this dashboard where we were ingesting about 10 million tweets every single day, and then geotagging them to different counties in the US, and then actually running our machine learning models on these tweets, and then predicting change in anxiety, change in loneliness on a daily basis, right? And we also could look at who's talking about different symptoms, right? How are concerns around COVID and mental health varying across different counties? So all of this was possible just using social media data. We got a lot of press coverage, but that's secondary. What was also interesting is the Department of Health in Washington State sort of reached out to us and asked us if we could share our estimates with the behavioral health team in the Department of Health. And essentially, they were reporting or using these indices that we created in their interventions, in their strategic plans, and so on. So that's the first challenge that I talked about, right? So are these measures valid? Can we sort of scale them? And I've tried to sort of convince you that they are valid and we can scale them. But let's look at the next challenge, right? So can we look at heterogeneity? And for example, let's just say we looked at Chinese Weibo, and we only found 6 mentions of people talking about, I'm diagnosed with depression. Does that mean that Chinese are not getting depressed? No, that's not the case, right? So base rates are not different. People do get ill, people do suffer from mental health in different cultures. They just express them differently, right? So for example, the self disclosure in certain cultures might be much higher than self disclosures in other cultures. Can we sort of tease apart these differences? So another question could be that, well, the base rates are not different, but we did look at how do specific events impact individuals. For example, the murder of George Floyd, which was 2 years back, we looked at how that impacts Black Americans and white Americans differently. And we saw that on an average, Black Americans have almost, I think, 10 to 15% higher response because of the in-community feeling that folks have. So we looked at the baseline depression scores in a sample of, again, 2,000 individuals recruited for a study, and we found that while depression rates are different by gender and age and education, so higher education, lower depression, but they don't really differ by race, right? So the base rates are not different, and yet the models that you train on one population don't necessarily translate to the other population, right? So for example, here's a model that we trained on the white samples. They do a fantastic job of, testing on white samples, but they don't really translate to Black individuals. Similarly, the vice versa, right? So you sort of need to have some personalization in training models if you want to be precise in diagnosis. So this is a paper that's currently under review at PNAS again, and we're also looking to expand this beyond the US, right? So for example, this is some work that was published in III SSSM last year, 2022, looking at urban and rural stressors in China. And now currently we have some work ongoing in India, looking at both Twitter and Reddit data and trying to get a sense of, can we identify hotspots of poor mental health using language data? So those are that was my talk, but I'll just briefly summarize the takeaways. Number one, if you're looking for final year projects or something like that, definitely consider these non-traditional sources. They're a fantastic low-cost resource to identify mental health, and AI-based tools can often be used in a very cheap manner, cheap meaning cost-effective manner across languages and countries. But at the same time, we need domain expertise and human annotations to often guide these models. We can't just, run a machine learning classifier on a data without actually knowing what we are doing, right? So we usually collaborate with folks in psychology and clinicians and so on when we're actually trying to apply these models. And that is, these are my collaborators across Penn, Purdue, and Stanford. And that's my team, and that's my funding. Thank you very much. I'm happy to take any questions now or on email. I don't know if you have time. Yeah, I usually try and wrap it up early. Thank you.
So thank you, sir. It was a really insightful session. Now I invite Dr. Neha Agarwal to present a memento to our esteemed speaker as a token of gratitude.
Okay, now for another great session today, may I invite Dr. Harshit Bhardwaj to present a sapling to our esteemed speaker, Professor Dr. Keith Sheringham. It is our great privilege and honor to have Dr. Keith Sheringham with us. Professor Keith Sheringham delivers business transformation for executive and senior management in blue chip clients across a range of industry sectors. As a noted author and speaker on the business application of ICT and a knowledge worker transformation around artificial intelligence, he has published thought leadership, peer reviews for leading publications, and has guest lectured at various universities in Australia and overseas. Dr. Keith is a company director and director for not-for-profits. Now I would like to request Professor Dr. Keith Sheringham to kindly address the gathering with his words of wisdom. Please, sir. Yeah, yeah, Keith Sheringham.
Good afternoon and namaste, and to if there's anybody else in Australia, good day. So this talk's going to be a little bit different because we want to talk about the business side and the opportunities that are coming down the pipeline around cloud, AI, and those sort of aspects. Now, I'm going to pose you a question to think about. You're the next generation of leaders. What is the positioning of India around some of the opportunities that we're going to talk about? And if you want to come up and give me the answer at the end, by all means, we'll see how we go. So we want to give a little bit of context and talk about technology. We want to look at some emerging opportunities. We want to look at some of the issues in how to achieve them, get into them in a little bit more detail, look at the role of government and the opportunities that lie there, and do a summary. We may have to fast track through some of this, but let's see how we go. All right. Who thinks we're living in an exciting, dynamic, vibrant time? Anybody? 500 years worth of change is happening in somebody's lifetime. This is one of the most dynamic times humanity has ever lived in. We have unprecedented wealth. We have unprecedented access to information, to solve problems, to create opportunities. So who feels confident about their future and the changes around technology? Anyone? One. Okay. Does anybody feel concerned that life's moving too fast? They can't keep up. They don't know what's going to happen. Two at the back, I love your honesty. Thank you very much. And who feels that they're not supported? Who feels a mixture of all three emotions? Beautiful. Okay, if we had a bit more time, we'd explore this a bit further, but let's move on. Whether we know it or not, or whether we like it or not, there is massive change coming down the pipeline. You are going to be impacted by technology through the services that you use. You already see the tuk-tuks now, they've got an electronic meter, they've got a Google map, and you've got that real cool barcode payments system. So whether you want to hide from technology or not, you're going to be impacted by the services that you use. Government is going to provide services using big data, analytics, and AI, and you're going to be impacted by them. And then there's how do we do the safety, the security, the protection? And whether you're a government agency, a small business, a medium business, a large business, or personally, it's how do we manage at scale the implementation and the outcomes? I'll share the slides with you three at the end, don't worry. Okay, is there anybody in the room who's a guru on quantum computing? Does anybody know what quantum computing is? No? Come on, you're IT computer design engineers, yeah? You should know 3 times as much about quantum computing as I do. Computing at the moment says yes, no, ones and zeros. Quantum computing is multi-state, so it's faster, quicker, that sort of thing. Now, quantum computing, once it started to get rolled out, can crack all of our existing encryption. The gurus tell me this. The American government has issued a mandate that by 2030, for national defense reasons, everything else, America has to be secure from quantum computing. That's 6 years away. Now, HSBC as a bank brought out in December the first standard for institutional banking FX trades that should resist quantum computing. Now, there's a whole bunch of implementation issues, there's regulatory, get all of that. So, quantum computing is going to impact us way before 2030. So, if you're looking to start your own business, you're looking for a career path, why not get into encryption and why not get into quantum computing? Because the demand is going to be there in 2-3 years' time, just as the time you graduate and you become the CEO of the next billion-dollar security company. So let's look at some emerging openings. Now, a little bit of a complicated slide. At the bottom, you've got the core platform off which society operates. Mobile computing, the internet, social media, and all of those ones. That is going to drive the entire society. That will be managed and operated using AI. Yes, we still have to manage some legacy bits and how we transition across is what we're going to have to work out. Things like infrastructure as a service, software as a service, platform as a service. Software as a service is Google Mail. That's all coming down the pipeline, and AI is going to get involved in that. Project management as a service, business analysis as a service, testing as a service. All of these services are going to be coming at you out of the cloud with new business opportunities around it. Take project management as a service, providing the software, the databases, the governance, the processes, the frameworks, the best practices, the routine admin to manage projects on demand as a service. Next one is the services coming out of the cloud. Who hates paying tax? Right. Who wants to work in tax? Have we got any budding accountants in here? Great career path. 3 career paths for you. High-end specialist advisory tax advice, having routine tax processing 80% automated with your purchases, your salaries being automatically sent to the tax office with your tax refund going into your bank account. There's not going to be many people doing that, but getting everybody else onto tax as a service, big career opportunities. And then you've got the machine to the machine learning and all of those aspects. Now, down the side, you've got risk, governance, safety, security, compliance, audit, resilience strategy, risk standards, accreditation. They're all going to be needed to be done. If the hottest job is the data analyst working for Microsoft at the moment, give it a couple of years, and the second hottest job is going to be the lawyer following them to sue them for the things that they've done wrong and to protect them from the lawsuits. Who wants to be an IT lawyer? No? Good. Okay. This is similar to the previous one, whereby you can see the increasing value across the page. You can see the different services. Now, one of the big ones is going to be industry-specific services that make use of AI. If you're in mining and logistics, sorry, transport and logistics, you're in mining, you already have the software. The AI is going to be folded into that software. Just as you have facial recognition on your phone, just as you have Siri on your phone, these are AI. You don't know that they're there, you're using them. So if you're a budding Indian entrepreneur, do you try and do AI and challenge Microsoft and Google? Do you do AI and fold it into existing applications across industry sectors? I'll leave that one to think about. Okay, we're already seeing gaps in AI. We're already seeing the downside of it. Who has faked their assignment for their course by using ChatGPT? Thank you for your honesty. I really appreciate it. We talked about tax. Now, have you had a cease and desist letter from your friends? For the more distinguished gentlemen in the front row who are over 25, have you had a cease and desist letter from your daughter generated by ChatGPT? We've already heard the horror stories, yeah? We've heard of court cases in the US whereby they created the briefs, everything on ChatGPT, they went to court and the judge threw them out. We've already heard the stories of Sony copying and pasting proprietary production code into a public system, not check it, and then even worse, put it into production. So we're going to have to address all of these sort of things. Now, one of the biggest ones is crime. If you're worried about your job from ChatGPT and AI, don't, because whether it's scams. I'll give you an example. The telcos now use AI to look at incoming SMSs, incoming phone calls, run AI across it and say, yeah, we think this is a scam, we'll push it to one side. Now, they're still getting through, but that's a huge area. Forget deep fakes in the American election. Crime always takes advantage of this technology. It's always ahead of the regulators and it's always ahead of the law enforcement. Now, please, I'm not encouraging you to take a life up in crime. I want to make that crystal clear, but I just want to get an opportunity out for you to think about. Now, one last one on this slide, the digital divide. In first world countries, it's still there. In developing countries, the digital divide is going to become a key issue. As we do more and more services out of the cloud, we do more and more AI, Those that are not able to keep up, not able to use it, it's going to be a gap. We'll cover off some of the stuff later. Now, what can we expect from all of this? We can expect new roles that we haven't even thought about are going to come down the pipeline. Existing roles are going to change. Sorry, some jobs are going to go away, but history tells us that overall there's an increase. Governments have to get in place with their policies, whether it's regulatory, defense and security, food and utilities. It's all going to be impacted by AI. Education is going to be the big one because where are we going to get the people from? Are they going to have the skills? Where are the teachers and the lecturers and the trainers to bring them the skills? So universities, you've got a whole lifetime of work ahead of you. Now, we research, we design, we develop, we test, we operate, we consume, we manage and assure. Those are the main roles that we do. All of that's going to be impacted by AI. So we're going to need a whole generation of new assurance processes to make sure that AI is delivering everything that we want and expect from it. Now, for those who fear their jobs, there's an aspect to that. The first strike related to AI has just finished. Screenwriters in America and the Hollywood Guild. Now, I know there was more to it, but AI was one of their fundamental aspects. So if you want to represent workers in a trade union, here's another golden opportunity for you. Now, one of the big ones is who's been on an aircraft? Anybody been on an aircraft? Right. AI is basically the pilot autopilot model. The pilot creates things for the first time. They intervene when things go wrong. They assure that everything's happening, and they manage the difficult customers. And the rest of aircraft aviation is automatic. That pilot autopilot model is what is emerging within most industry sectors around AI. Let's skip that one. Let's explore some opportunities. So you're going to use public AI services. Large organizations are going to have their own private AI services. So if you're Enron, you will have your own instance of ChatGPT running. Hospitals, it's the same. AI is going to get embedded into a whole bunch of areas as well as being standalone. It's going to be the sector specific. Now, one of the big ones is open loop and closed loop data. You've probably experienced this with the medical ones, where it's a relatively closed loop with the relatively controlled information sources, relatively controlled quality. AI works really well. Advertising on Facebook and social media is another example of a closed loop. You've also experienced the open loop where you've tried to pull in 30 different data sources and you've had access issues, quality issues, permission issues, and that sort of thing. AI is breaking down at the moment with open loop data. And there's a huge opportunity to build the next generation of apps that will address data management issues. And that's not just an Indian market, that's a global market. Let's move on. Conscious of time. So how are we going to manage and realize some of the opportunities? We're going to have to manage the community response. India did some agricultural reform and it wasn't well received and it had to wind it back. And it happens in many other countries. You will need to take the community with us on the AI transformation. There's going to be government policy, there's going to be education again, and there's going to be the business management issues to work through. So some of the bits that we'll need to put in place is how we manage things, change the environment, instill the behavior, manage the outcomes. Leaders will need to be the change they wish to see and treat others as you would be treated. One of the other ones is consistent and persistent application of proven business principles to manage the outcomes. You cannot just roll out AI if you don't have a business case and you can make money on it. One of the concerns that they're already starting to have with players like ChatGPT, despite all the money backing it behind Microsoft, and I know it's early days, they don't make money. So more opportunities for you. Let's explore some. So the traditional, if you're a first mover, you're going to get the competitive advantage, you're going to challenge the incumbents, you're going to do your mergers and acquisitions. Changes in technology do one of two things to an incumbent. They either make it redundant or they strengthen its market position. So if an incumbent responds quickly enough, fast enough, embraces the technology, they become a bigger player. There's all the opportunities around the business changes, the new businesses, the changing businesses, and there's all the emerging opportunities like sector-specific AI, AI embedded within solutions, assurance services, data services, and supporting the operations. Let's skip through because we're running out of time. Let's talk about education. We're in an education institution. They do three things. They do teaching, they do advising, and they do research. Teaching is sort of guaranteed revenue streams, low risk. Research is higher risk and has a higher insecurity. And advising, you've got to go get your own money. So real-time decision-making, automation, cloud-based services, and personality assistance are all emerging areas. As a university, Amity has to fix its own operations around AI. It's got to teach it, it's got to advise governments on it, and it'll do consulting services as well. So if you think education is going to be a backwater, sorry, very different story. Now, in the transition, you have to keep running your business. If you process mortgages, you manage investment funds, you still have to keep managing those whilst you change the business. That's an issue for resources, budget, and all of those things. Now, there's going to be three main streams coming through. One is the technology, the data, and the operations. One is all the products and services and the regulatory. And the third stream is the skilling, training, accreditation, and certification. That is a big opportunity for individual entrepreneurs, organizations, as well as universities. Let's skip that one. Now, there's a one takeout message from this complicated slide. Who's heard of SWIFT payments? Right. For those that don't know, SWIFT is all the banks globally got together, set a standard so they can make payments. What they did is they built a bureau model, and they do accredited training and certification for everybody to use SWIFT. If you're going to build the capacity and capability within the mining sector around AI, there is a benefit of the companies getting together, adopting a SWIFT bureau model, and doing the accreditation, skilling, and training to uniform standards, building up the base within the industry, making it easier for people to move roles. Now, it doesn't stop there. Agriculture and agricultural practices, whether it's farming, you name it. Pharmaceuticals and the manufacture of pharmaceuticals, assuring quality in that one. big opportunity for the entrepreneurs in the room to get into the Swift Bureau model. Now, we research, design, develop, test, operate, consume, manage, and assure. And there's a whole series of jobs coming within those different areas, both in run the business and change the business. Pity we don't get time to explore them, but that's all right. Now, has anybody worked for or knows anybody that works for Tata? Tech Mahindra? HCL? Right. Indian IT companies have been very, very successful. And whilst they're moving up the value stack, they're still mainly doing routine code, routine operations. Now, defect and enhancement, account management changes, all of routine data processing, they're going to get automated by AI. So where is Tata and the other guys going to get their revenue opportunities from? I'm sure they're working on it. So things like project management, advisory, application migration, they're all areas that are going to come through. Application migration integration is a huge area. Why? Because AI needs all the information from a whole bunch of disparate systems to work. There's all the technology services that are coming, and then there's the risk, the audit, and the security that we've talked about before. So again, there's a whole bunch of existing operations and services that will need to be extended to support AI and data in the cloud, as well as new ones that come through the pipeline. Now, there's a couple of emerging areas there. I'm going to pick one, because we're doing okay for time. Personality assistance. Now, we've all watched the Bollywood movie and the Hollywood movie, and the person knows exactly what to say at exactly the right time to get the exact response that they want from the person and them to do it. Real life is very, very different. Now, park the regulatory, park the privacy issues and that sort of thing. AI has the ability to go through massive data sets and create personality profiles on you. So I can be at a party, trying to get a date, search through, oh yeah, this is their profile. I can talk to them and it helps me do that. Whether I want that to happen, I don't know, but let's not worry about it. Combine that with IVR software. So when you're ringing a call center and you're working in the call center and the person's yelling and screaming at you because you haven't fixed their problem, they can be using AI to help them not only diagnose the problem, but manage you through the process, get you to calm down, get you to be nice, those sorts of things. Tie that in with facial recognition, tie that in with a bunch of other technologies. It's a huge area because it's got so many applications. You'd use this in your research. Now, again, park the regulatory and that stuff for a moment. This is an opportunity that is going to come down the pipeline, whether we want to or not. Yes, it's going to be managed. There's going to be restrictions. So do you, as budding code cutters and entrepreneurs in the room, is this something that you want to do, get into, and steer your careers in that direction? So do you want to create the next Tech Mahindra doing data management and personality profiles? Okay, data management. As soon as somebody says data management to me, I yawn and fall asleep. We all know the problems. You've got spatial data, unstructured data, structured data, the metadata, the permissions, and that sort of thing. Data's got to be migrated into something that AI can use. So whether it's field matching, entity matching, naming conventions, standardization, there's a big gap to address. And we're already seeing that with existing AI. Forget the AI coming in 10 years' time. We're starting to see this gap now. We share data across channel partners, third parties, government agencies. We've got synchronization issues. We have storage issues. We have recovery, but you've got archival issues. If you're in healthcare, you're in law enforcement, depending upon the regulatory regime, you may have to keep records for 10 years. A court case has to be kept in Australia for up to 100 years in case that gets opened up. So there's big opportunities around sharing of data. And then there's all of the operational aspects like permissions, privacy, and that sort of thing. So who in this room sees themselves creating a billion-dollar enterprise with specialist software supporting the data that feeds into AI? Forget the AI itself, but who sees themselves running a billion-dollar company addressing data management? And it's not just an Indian problem to a market of 1.2 billion people, it's a global market. Now, who uses Facebook? Right. Who heard of the famous case where Facebook was sued by a parent because their teenage daughter was getting depressed? You know this one. Facebook showed that if they change their algorithm, they get less advertising revenue, but people don't get depressed and suicidal. Now, I can't blame Facebook for having a winning strategy and going back to their old algorithm. AI has two component parts, the data and the algorithms. If we're using the algorithms, we have to know that they're learning the right thing. We've talked about the data quality issues and the use of AI in them. Now, if we're processing mortgages and rejecting people's mortgages on the basis of shonky AI, yeah, we take a hit, we pay a fine, and we're gone. When people start dying, it's a very different conversation. So one of the big opportunities still to be figured out is benchmark testing of AI, both on the data side and on the algorithm side. And whether you're into the design and development, whether you're into the auditing, whether you're into the accreditation and certification of it, again, this is a massive area that is still to be unpacked. We don't even know yet enough about how to do benchmark testing, yet alone using AI to benchmark the AI. So there's a lot of research opportunities for people in the room. Risk management, again, a whole bunch of services coming up in there. Now, we've sort of covered service centers a little bit, which is a big piece in India, and the use of profiling, and we've talked about data migration, so we'll move on. We've talked about the criminal opportunities, and let's explore that a bit more. Billing and charging, frauds and fakes, theft, terrorism, sanctions, bribery, and corruption. These are all things businesses have to deal with, especially global companies. They have to worry about sanctions, especially banks and financial services. AI is being used right now to defraud banks, and banks are using AI to try and stop that. Huge opportunities coming again. So we've talked about some of the business opportunities and that sort of thing. I've got a few moments left. I want to talk about government. Whether you are a democracy or a totalitarian regime, images, videos, deep fakes, offending the dear leader, not offending the dear leader, against your political opposition, we're going to have to deal with it. We don't have most of the answers yet, But again, it's another business opportunity. And you, as you go forward, is this the business opportunity that's going to make you famous? We've talked about social media and the misinformation, targeting, campaigning, and media monitoring, all areas with AI. Now, one of the biggest players in AI is not Google, it's not Facebook, it's not Amazon, it's not Apple, it's government, whether at the state, federal, or municipal level. They have to make their own transition, and they're going to need help to do it. All of the services that they provide to you, ports, trains, sewage, water, they're going to need help to transition across. Governments will need to do grants, tax changes, incentives to have AI build. And if the Gujarati government wants to build technology parks, let's say, and they want to go down the data path, then government will be doing the incentives to get the rewards on the economic back end. And regulatory and enforcement is going to be a big issue. Whether it's your license and your permits, whether it's national defense, whether it's security, public safety, the prosecutions in courts. A simple thing like what evidence they can play in court in a prosecution to win the case or, defend the case. Big challenges coming down. Again, there's a massive opportunity in services to support government. Now, government has to manage societal uncertainty. It has to manage crime. It has to manage the disruption and everything that's coming down the pipeline. It has to provide the leadership to the societies, and it has to manage the response. So if you're an aspiring politician, here's your roadmap. So let's summarize. When technology transformation becomes a national security issue, when it becomes an educational priority, and when politicians campaign on economic transformation, not against it, but for it, you know that you're going to be well into it. You've got to have the policies, the education, the leadership, and government funding, and how it does it is going to be a key aspect. Now, I want to just spend 2 minutes on this slide, and then we'll wrap up. So, this is remember I asked you at the beginning of the question around how you see India positioned for technologies. How these pan out, let's not worry about that, because some of them may not have a business case beyond them, some of them will. There's the embedding of AI within routine IT operations and services, enabling people to be freed up and to move up the value stack. That's one area. So having the AI written so that the routine server administration can be managed totally by AI, one opportunity. Realizing all the services and opportunities around AI, which we've sort of covered off. We've talked about solutions for data provision, data management, and data quality. We've talked about benchmark testing. Now, we've talked about integration of systems, and that needs to occur, and how there's going to be a next generation of technology for integrating systems. One of my questions, I'll come to that, and then there's a revision and consolidation of application information sourcing. At the moment, we have an operating system and thousands of apps. There's an app on here for everything. And I know this is underway in different levels of maturity, but why do I worry about applications? I worry about applications because that's how I get information, and that's how I manage a process. With machine-to-machine learning, machine-to-machine integration, facial recognition, IVR, there is no reason that your phone will be like this in 5, 10 years' time. It may be, I don't know. But my question for you as budding entrepreneurs and computer scientists, are you going to write the next generation where data, systems, applications, and operating systems you don't give a damn about? Huge business opportunity. Now, last one. Sell the shovels to the gold diggers. In a gold rush, people got a shovel and dug for gold, and some of them made their fortune. The people that made the most money were the shopkeepers selling them shovels, groceries, water, bedding, and everything else. Does India want to be the gold diggers, or does it want to sell them the shovels? That's another question for you all to take home. Okay, let's wrap up and share the slides. There's a couple of links there for more information. And let me say thank you very much indeed. Thank you for listening. It's been a privilege and a pleasure to do this. Quite simply, I don't get to do many of them coming from the business side. We've got 5 minutes for questions, comments. Let's throw it open to the floor. The back row, you raised your hand and you were nodding very wisely at times. Any questions? Any comments? Yeah. Sorry, can you give him a prize for the first question?
Sir, I wanted to ask the same question which you asked us. What will be technology after 5 to 10 years?
At the moment, India is positioning itself well, but there's a huge gap still to do. Not knowing enough about some of the aspects that goes on in the economy. I'm not seeing the Indian tech companies moving fast enough around some of the new opportunities. They may be, and I just haven't seen it. India has this massive potential in these emerging areas. India's been very, very successful, but it's been at the low end of the technology value stack. Yes, they're doing Tata and those guys are doing bits of it. The small companies are doing bits of it. The business transformation side, the regulatory, the risk, the audit, they're not players. And you should be. And you should be players in some of these, if not all of these, because they're not just an Indian market of 1.2 billion people. It's a global market and the opportunity is there. And if I was in Australia, I'd be having exactly the same conversation. Does that answer your question?
Yes, sir. Thank you.
Thank you. Sir, sorry, no prize for you.
So what about the fact that could India be not only the gold diggers and also the shovel suppliers and also the persons who provide the material to make the shovels?
It should be doing all three. Great point. Should be doing all three. So over lunch, we were chatting to India starting to build its own supercomputers. But it started, but it's early days yet. And you're absolutely right. They can get the biggest bang per buck selling the shovels. They can get money out of being gold diggers. And if you integrate the supply chain, you know, you've got the platinum dug out of the ground, made into catalytic converters, shoved into the car. Ford, all those guys control the whole stack. Yeah. There's opportunities for India to control the whole stack. Oh, and by the way, the US is tardy in this area as well. Australia is, so is the US. Sorry. Good. One more question, please. Who wants to go to Australia? Good. That's the final question. Thank you very much.
Thank you, sir. It was an amazing session. I'd like to invite Dr. Neha Agarwal to present a memento to our esteemed speaker as a token of gratitude.
Thank you, everyone. Hope you enjoyed it. No, it's okay. I already have too many. My bag is thank you.
Being settled, the session is yet not over. You're requesting to please be seated.
A very good afternoon to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Vansh Tiwari, student of BTech Computer Science, express a warm welcome and respectful welcome to the 14th International Conference 2024, Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, MIT School of Engineering and Technology, MIT University, Uttar Pradesh, Noida. As one of the leading global universities, MIT University is dedicated towards its responsibility of imparting its student with a strong foundation and a platform for the empirical equation. With this agenda, Conference 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new direction in the field of next generation technologies. May I invite Dr. Anant Kumar Jaiswal, Professor MIT University, to present a sapling to our esteemed speaker, Professor Dr. Chandrajit Bajaj, University of Texas at Austin, USA. It's our great privilege and honor to have amongst us Professor Dr. Chandrajit Bajaj, University of Texas at Austin, USA. Professor Dr. Chandrajit Bajaj is a distinguished computer scientist and an academician, currently serving as a computational applied mathematics chair in visualization and professor of computer science at the University of Texas. He is also the director of the Center for Computational Visualization at the University of Texas. His research interests span across geometric modeling, imaging data science, bioinformatics, and data visualization with an index of 73 and 21,219 citations. He has held several faculty positions in computer science at Purdue University and Cornell University before joining the University of Texas in 1997. His research has been in the fields of computational biology, geometric modeling, image processing, and computational geometry, computer graphics, compression, mesh generation, scientific computation, and visualization. He is a current editorial board member for the ACM Computing Surveys, the International Journal on Computational Geometry and Application, and the SIAM Journal on Imaging Sciences. Professor Bazar is a fellow of the American Association for the Advancement of Science, the Association for Computing Machinery, the Institute of Electrical and Electronics Engineers, and the Society of Industrial and Applied Mathematics. He has received numerous accolades, including the ICES Sid Manosev Grand Challenge Faculty Research Award in 2009, 2011, 2016, 2017, and the Distinguished Alumnus of Indian Institute of Technology, Delhi, India in 2016. Now I request to chair Professor Dr. Chandrajit Bajaj, University of Texas at Austin, USA, kindly address the gathering with his words of wisdom. Please, sir.
इसको खाली कनेक्ट करना होगा
Hello. Sorry to keep you waiting. So this talk is perhaps different from other talks you've heard. So rather than talk about the newest applications, this is more foundational. Think, how do we learn and how can we learn better? And how can we program computers to always keep learning, just like we humans can always keep learning? So maybe I'll repeat it because I was not loud enough. So this talk is about foundational learning or foundational AI, as they say. There are some people talking in the back and they probably can't hear me. So if you give me 20 minutes, I'll only take that much time. And I'll tell you about this idea of how we could learn in a more principled way. And how can we program computers so that they can actively and continually learn? So learning is something that's inbuilt to our psyche as humans. And there are many other species that learn, but there are some that don't. There's this nice story that I learned when I was a child of a heron sitting by the lake waiting for fish on the quiet side of the lake. And it would wait sometimes for hours and only then catch a fish. But that heron also saw some school children going in the evening who would throw pieces of bread into the lake. And there was always activity. So one day the heron flew and picked up that piece of bread and brought it to the quiet side of the lake and dropped the piece of bread and immediately caught its fish. So what's the moral of the story? The moral of the story is the heron learned something, learned how to improve its task of catching fish. But what is the unfortunate part of it? The heron has no mechanisms to teach its young. So its children have to learn by themselves. We as humans have the advantage that we have teachers who will guide us and teach us. And that is something that we should leverage. We should constantly leverage of persons who are willing to teach us so that we can get better and sometimes not only equal them, but even get better than them. So this is a story that also goes back 400 years. From the time when people were trying to think about how the universe and how our planets moving in the solar system. And it was only later that Kepler was a scientist who discovered the laws of planetary motion. But before that, there was Copernicus. And they had thought about that the sun was rotating around the earth. And all of Christianity also felt that the sun was rotating around the earth. It was only later that through the early data scientists, a baron called Tycho Brahe in Denmark, who spent his fortune just capturing data. So he had a lot of telescopes that Galileo had built, and he captured how the planets were moving, whatever that was visible, and that data is what Kepler used to come up with Kepler's laws of motion. Another very famous scientist is, of course, Newton. And the story is that apple fell on his head, and so he learned force is equal to mass times acceleration, and torque is inertia times angular momentum, right? But that's not how it is. It is looking at observations and data and saying, oh, I wonder what can I write down mathematically to model that? So computers are able to model, not learning how to solve an equation, not learning how to do calculations fast. Because if I say, oh, I can learn how to multiply two matrices, saying, okay, well, can you learn any two matrices? It says, no, if you give me two small matrices, I can go back and give you the answer. Then he says, what about if I gave you 500,000 by 500,000 matrix multiplied by another 500,000 by 500,000? And I don't want to wait forever. Or he's saying, oh, I have to come up with a new algorithm, a new way to do it. That's learning. That's learning so that you become the guru and not having to go to the guru every time and say, give me an answer. Because the guru has learned the rule. So this is what we should start thinking about, saying, how can we make computers be programmed so that it will always keep learning? On the left, what you're seeing is an old way of machine learning. It's the classical way. I give you a picture and the computer says, oh, this is a cat, this is a dog. And here's a mask of the cat, and here's a mask of the dog. This is like kindergarten. You say, tell me, what is this? Oh, this is an elephant. No, 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 you got it wrong. This is not an elephant. And you learn. This is what we do in kindergarten. So if machine learning was only the left-hand side, then it's a very primitive learner, right? We want them to become equal to us so that they can help us and even do tasks that we can't do properly. So that learner should accelerate through kindergarten to 12th grade, through college, through university, get a PhD, all in rapid time. Is it possible? Answer is yes. Why is it possible? It's possible because they're supercomputers. They don't have to eat or sleep, or they can work 24/7. So if they are going to work at such superhuman speeds, then they should get very good very, very quickly. How do we program them to become such principal learners? On the right is a more strategic way of thinking of it. So look at this animation of a molecule. It's a virus. It infects bacteria. Viruses are parasites. They cannot replicate. We humans can replicate, right? We've got something called the ribosome. Viruses don't. So they inject into a host cell, put their genome into it, and then let the machinery of the bacteria to replicate. So they've learned and evolved as a chemical to replicate. This evolutionary principle is something that people try to learn from and saying, how does a chemical from nothing suddenly start to evolve and become better and better and better and better? So by the time it can be so dangerous as an HIV virus. You know why they call it the HIV virus before the SARS virus and so on? HIV is human immunodeficiency virus. It's like a Trojan horse. It infects the very immune cells our bodies are made of. And it injects its genome and retrofits its genome completely unknown to the immune cells into the T cells. So whenever you get infected, the T cells are unaware that they've been infected. But if the human is infected, our immune cells, which has evolved from so many years that protects us from all the bad things we eat and still we can survive, that infected T cell, instead of producing antibodies to remove the bad in our bodies, is making multiple copies of the virus. So it's like a Trojan horse that has infected it. And this Trojan horse mechanism is a very complicated mechanism. But you wonder, it's not alive. Viruses are not alive. They are just chemical forms. How does it evolve to becoming better and better? That secret is the principle that once we learn, we can program. And we can make computer programs evolve to get better and better. There's a responsibility, and that responsibility is of not doing something bad for humanity. Okay? So rather than make a long story short and get too mathematical, here is what people have discovered over time. This animation you're seeing is of hemoglobin. It's a magic molecule inside our body. It's what makes humans as big as we are. Otherwise, we'd be like insects, only breathing through tracheal tubes, right? Insects have blood, they have that, but they don't have hemoglobin in the blood. Our hemoglobin allows for transport of oxygen and carbon dioxide from our lungs all over our body, wherever the muscles need oxygen, the heart needs oxygen. So hemoglobin is magical in that it can absorb carbon dioxide, take it to the lungs where you've got fresh oxygen, it'll release the carbon dioxide, quickly grab oxygen, bring it back to through the power of the pump, which is the heart, to provide oxygen to those regions that are there. A magic molecule. Again, evolution has occurred by something mathematically called the Hamiltonian. So what is the Hamiltonian? Again, I'm going to skip over a few things, but one of the best things to understand is what people started to question. Time for a lot of people is very valuable, right? They can't afford to, do something at the right time. They will say, oh, let me check my email. Let me get focused on checking my computer for some information that I can browse through. But in one sense, if you're doing a task, you should be looking at it in a space-time continuum. The space-time correlation is what is called the Hamiltonian. So what you're seeing here is a molecule that learns through interactions with the environment of getting better and better to preserve itself, to bind to the right thing. It's doing it all by interactions with the environment. Next time you want to learn how to ride a bicycle, what do? You might get a coach and a friend to help, or your parent, but you have to keep trying. The more you try, suddenly you discover how to balance, how to go back and ride the bicycle. That's what the molecule is doing. It's interacting with the object and the environment continuously with one fixed rule, which is what we try to do. We want to improve. So every time we interact, we go back and say, oh, what did I do wrong? Let me go back and do it right. And what I did right, let me reinforce. Hence was born something called reinforcement learning. So in reinforcement learning, what you do is you don't choose a model. You learn to always interact with the environment. And if you do it right, you get a reward. If you do it wrong, you get penalized or you don't get a reward. You get regret. So I could have won $10 there, but oops, I didn't do it. I didn't interact with the environment. I'm going to only get, or I made a mistake, I'm going to get 0. So Through this formalism, this cart pole learns by itself. I can write a program that makes this cart pole balance. This might seem very simple, but it's actually not a trivial problem. How to balance something so that it doesn't fall over by its weight is a complicated thing that we learn to do. This mountain car you're seeing learns by itself to climb the mountain. What it has the power to move forward or backward. It can move with a certain velocity. It can learn how much velocity it has to move. All of these are parameters of the program. But starting from scratch, it'll learn how to climb that mountain. It's the same way of saying, I can learn to climb Mount Everest. I might not do it in one shot, but I'll do it after many attempts. But before I climb Mount Everest, I'm going to learn to climb a smaller mountain. And once I learn how to climb a smaller mountain, I can learn again to climb a better mountain. Hence comes the fundamental rule, we call it black box optimization. And the method of black box optimization by which you can optimize by learning your mistake and then correcting your mistake and learning it better. Learning not to make the same mistake repeatedly. If you always improve on some mistakes, of course, you're going to reduce your mistakes. Hence, you will get better. And learning is not just doing a task. Learning is learning how to do a task you have not done before correctly. So you're learning to be prepared for something you have not seen before. And the philosophy here is that of balancing it with something we call optimal control. Saying, if I'm going to solve an optimization problem, saying, I want to be the best on this task, then I have to learn how to move forward. But I also want to learn to move forward with the right decision making. So I'm not going to only go back and do a task and measure the loss at the end and then use it to correct my task technique. I'm going to take everything along the path and say, where did I go wrong? And where I went wrong is where I want to correct. And where I didn't go wrong, I don't want to. Imagine you trying to learn how to drive a car. There's many a time that you would say, hey, just keep your eyes ahead and at least move the car 5 feet forward. I know you have to go 1,000 feet or 1,000 meters ahead, but go first at least for 10 meters or 5 meters. Once you learn how to go to 5 meters, then you can go to 10 meters. After 10 meters, you can go to 20. And suddenly you start learning how to go to whatever lengths you want. If you want to swim, the entire line of the Ganga from the Himalayas all the way down, you can't learn to do that in one shot. If you want to learn to fly a plane, you can't say, I can be expert in flying a plane in any weather. So what you want is to progressively keep increasing your environment's complexity. And that is this notion of reduced Hamiltonians or progressive Hamiltonians. I'm not going to bore you with the mathematics because a lot of you, it's time for you. You've been attending the conference the whole day and it's time for dinner. So I'll just give it to you in a gist. These pictures on the bottom are saying the mountain that I want to really go down is the one on the right? But what I'm going to first assume is the mountain on the left. Very simple mountain. And if I can learn to go down the bottom of this mountain, then I can progressively increase the complexity of the mountain, each time learning how to go down the mountain. And this piggybacking is a principled way of doing it. Again, I'll skip all this and perhaps tell you about what we call a surrogate model. So a surrogate model is every time you have a task you want to learn, in your computer, you program to make a simple task, solve that simple task, then make the task more complicated and solve that more complicated task. And if you progressively go through the cycle, you start getting better and better and better. And it's not that everyone has to go through grade 1 and then grade 2 and grade 3 and grade 4. Suppose you're very good in grade 2. You might skip a class and go to grade 4. Similarly, you have to have the ability for the program, if it is learning a certain curriculum, it can learn to go speedily, customized to its learning ability. And this is what we call the optimal control flow algorithm. Again, I'll show you an animation. Each time I go down this mountain, minimizing this objective function, I learn something. And the mountain's complexity can be increased because I've become better. I don't want to do the same thing that you tell me to do when I was in grade 1. Saying, hey, treat me as an adult. I'm in grade 5 now. Saying, okay, well, now you're in grade 10. I need to treat you even more. So as I raise your learning complexity, your ability to get challenged and learn progressively will always increase. And the task is always continual. There's no reason to stop learning. You can always keep your programs to learn better and better and better. So programming machine learning, not just by using libraries, but thinking about these fundamental foundational paradigms is the message I wanted to give you today. So in this training task, this program successively reduces its uncertainty. These bands I'm showing you is the uncertainty it has of doing this task right. So such is the method by which at the very beginning, you would be scared if you wanted to drive at night because of blinding headlights. The risk is too high. But eventually, as you get better and better, you as a human can probably go through Delhi traffic in the night, right? Same way is how we learn to write programs nowadays. Our programs are constantly learning, adapting, understanding more and more complex environments and starting to get what is called Superman strength. You know, I give an exercise in my class of writing a chess program. For many years when I was young, your age, we used to write chess programs so that they could beat a human. And people built supercomputers. IBM had this big challenge to write a chess program that could beat the grandmaster, right? Nowadays, you can write one. And in less than a week of computing time, that program will become better than a grandmaster. Guaranteed. It will also keep increasing its strategies. One of the strategies that came out of this was in most programs which were to train, there's in chess, you have what's called the castling move. You protect your king by castling with the rook, and you protect it with a bishop and a knight. For those who haven't played chess, go and look it up. The best moves that won and beat the grandmasters in chess and then also in Go were strategies that were completely different, completely generative. Generative means they were not taught, but the computer learned to come up with a new way. It used its king and queen to move around, protecting. And once the pawns guarded by the king and queen moved to the other side, they became newer queens. And that strategy beat every grandmaster over time. Nowadays, there's no grandmaster who can play against a computer program which is intelligently trained and win a championship because of this continual active learning ability. So what I'll stop with is just to share this fundamental paradigm that we as humans are clever. We take lessons from nature, we take lessons from teachers, and continually adapt and become better. And if we can write programs that have this ability, then they will always become useful. There's always the ethical side. Don't do anything which will cause harm. And that has to be self-conscious programming by yourself. So this is an example of the car that learned how to climb the mountain, just like what I'd shown before. But there are many, many other phenomena. So here's another project that we work on. It's called tetralogy of Fallow. I don't know how many people know about how the heart is created in your body. It's a pump that is going to last your lifetime. Most heart replacements don't work, right? Your brain is also very expensive tissue. You have it only once in your lifetime. So these expensive tissues, unlike maybe your skin, if you tear your skin, it'll get repaired. These things will not. But with computers, there was this thing about how the heart was created. It was created by two small tubes in the embryo that fold up like balloons and form 4 chambers. And a good heart would have a left ventricle that would pump, a left ventricle and a right ventricle. The left ventricle would pump oxygenated blood, and the right ventricle would pump deoxygenated into the lungs. So one goes into the lungs, the other goes into the rest of the body. But during this genesis process, there used to be times when the children are born with holes in their septum. That means it's a leaky pump. Most of the time, this would cause other problems, and that's why it's called tetralogy of Fallow. And the old way of doing it was reconstruct the heart and then try to simulate blood flow through it. Today, with AI, you can just use cardiac imaging and ultrasound and directly customize what is the problem with this child while the child is still in the embryonic state. So this is the promise and the magic that AI can bring to the table, but it requires principled ways of programming it. And if we are bright, we can. And if we are, just going to follow the old methodology, then we'll plateau in our abilities. We can't keep getting better and better and better. So with that, I'll stop and take questions, if any, and thank you for your attention. Any questions? No? I don't have any prizes to give. But any thoughts that you have, this is a good time. It doesn't have to relate to this talk. Yes, go ahead.
I have been wondering for a week now. The project that you shared, I wanted to know how did you come up with the problem statement in the first place is why you were discussing and which is secondary thing. But a very basic question that every student I think has and they wants to get into is how do you look for a problem statement?
What you're saying is also partly what I tell everyone is understanding what is a problem is like 80% or 90% of the work. So a problem is not just any question. A question that you have is saying, how do I do this? Saying, how has anyone else done it? Learn from the people who've gone before, because most questions that you've come up with have come up, others have also thought about it, right? So learn, there's an old saying also that I can see further because I'm standing on the shoulder of giants, right? Saying, no, it's not only standing on the shoulders. Learn to climb onto their shoulders. So the way you find a problem is by asking the question, see how else has anyone else solved the problem. And if that problem is solved completely, make the problem harder or make the question harder, saying, okay, you can do this thing, but can you do this? So that's piquing your curiosity to why you asked the question and then asking a more difficult question and seeing that, yes, no one else has solved this adequately. And suddenly you have a live problem on your hand. And you're the first to solve it, and you become famous because then everyone else will say, oh, we need to learn from you, right? Any other? No? Yes. Yeah. So his question is, he was wanting to work on a problem of brain tumor detection, right? And lack of data is an issue. Nowadays, if you scour the website, there are many resources that are made for humanity's sake. NIH is a big institute, National Institutes of Health in the United States. It funds universities and companies just to curate and provide this data. So for brain tumors, you have to necessarily look at MRI. And then if you just search for MRI, you will find many resources. And look for what are called PubMed resources, public medical resources. Okay? There are many to train with. And what others do also when they provide solutions, they sometimes label the information and also show why their solution is better than previous. And that data is also made available, right? Many GitHub resources. So that's where you would go into. Last call, no more questions. Oh yes, one more, go ahead. So AI is such a broad term. You think of it as artificial intelligence. I think of it as actionable intelligence. And the reason being, you want to come up with not just one decision. You're continually making a sequence of decisions. Even your idea of trying to go from here to your hostel, you might suddenly be encountered with a situation, there's a crowd, something unforeseen. So you have to make a decision. Should I go the other route or should I go here? Right? So AI, actionable intelligence, allows you to make a sequence of decisions, and you should optimize over that sequence. And this is relevant for any industry. Businesses, economics, your own lifestyle, your studying, and so on. And that is starting to come up now. One of the other big areas is the space of possibilities that you're learning and training for is small in small tasks. But suppose you wanted to learn a automatic learning how to fly an aeroplane, as an example, saying, what's difficult about it? Is it as difficult as driving a car? Saying, in some sense, yes. Why? Because the environment and the situations that can happen are infinitely larger, right? You can't learn every situation that happens. So when that, what we call phase space, is so large, your ability to find the best pathway for a sequence of decisions is something that you will keep improving. You can keep getting better. That area of research is going to become very big. Okay? Yeah. Oh, yeah, we have to go there. So I have to go. Thank you for your attention. Goodbye.
Thank you, sir. May I invite Dr. Anant Kumar Jaiswal, Professor, Amity University, to present a memento to our esteemed speaker, Professor Dr. Chandjit Bajaj, University of Texas at Austin, USA. May I invite Dr. Anant Kumar Jaiswal, Professor, Amity University, to present a sapling to our esteemed speaker, Professor Dr. Abhinav Bhatle, University of Maryland, College Park, USA. It is our great privilege and honor to have amongst us Professor Dr. Abhinav Bhatle, University of Maryland, College Park, USA. Professor Abhinav Bhatle is an associate professor in the Department of Computer Science and director of the Parallel Software and Systems Group at the University of Maryland, College Park. Now I request to Professor Abhinav Bhatle, University of Maryland, College Park, USA, kindly address the gathering with his words of wisdom. Please, sir. Thank you.
Is this still connected? Can you take me to that? Okay. Oh, did you move it somewhere? No, I moved it to the next one. Yeah, there's stuff. I don't see it. Let me get it again. 1 second.
Okay. Wait, can I open that with some other? I don't know. Okay, I can only open it here. Okay. And yeah, can you start the screen sharing? Yeah. And it's not showing up there. It's not showing up there. Bunch. Okay. And how do I full screen this? Okay, hello everyone. My name is Abhinav Bhatele. I'm a professor at University of Maryland. So let me first see how many people are everyone here in computer science? No? What other departments are here? Okay, and in terms of first year, how many first year students? Second year? Third year? So mostly third year? Fourth year students? Okay, how many people have heard of AI, artificial intelligence, deep learning? How many people have heard of high performance computing or supercomputers? Okay, so my primary field is high performance computing, supercomputers, and my talk is going to be about how do you merge those two areas, AI or deep learning and HPC. Yeah. So I'm going to skip some of these slides. This talks about where high performance computing is used. So some people said biotech, it's used a lot for molecular dynamics. That's the first image, weather forecasting, study of the universe, cosmology, and so on. And these are the kinds of computers that are used. You have lots of CPUs and you connect them with a network to get a large supercomputer. This is a list of the world's largest supercomputers, thousands of GPUs and so on. Now, what's happening today is there's an ongoing revolution. You have lots of data sets, you have improved GPU machines, and you can use them to train deep learning models, right? Okay, so there's a convergence happening between high performance computing and cloud computing and AI. And the question is, can we use large machines or cloud computing to train AI models faster and faster? So, okay. Is everyone familiar with what a deep neural network is? So I'm seeing a lot of muttering here in the background. Can we get attention to the slides here for 15 minutes and then we'll be done? I think this is the last slot, right? Okay. So deep neural networks are like, I'll probably skip over some of this, like Professor Bajaj was talking about. You're trying to learn something, right? So this is what a neuron looks like. It tries to mimic a human neuron. You have some inputs, it gives out an output, and there's a function that tries to learn something about the inputs and generate an output. When you connect many such neurons, you create a deep neural network. It's called a deep network because it has multiple layers. And you do some computation on each neuron. And then when you combine all of this, you get a deep neural network. Now, since there are individual computations happening on each network, if you do this in parallel, you can get speed ups from being able to do things faster. So in fact, many researchers have been doing this. They've been trying to make deep learning faster. That's how you're getting faster and faster models. Do people use ChatGPT here? Do you guys use them for your homework or assignments? Okay, so all of it is powered by a deep learning model, right? People have trained a model, they have weights stored on some machine, and when you log into ChatGPT, in the background, the model is taking those weights, coming up with new outputs for whatever you're asking, and then generates something, right? So since people have large compute power through GPUs, they're able to train larger and larger models. The largest models today are billions of parameters, right? So GPT-3 is on the chart here, which is maybe around 100 million parameters, but GPT-4 is supposed to be around 1 trillion parameters. So the question is, can we use parallel computing to train things in parallel? There are many approaches already. So the most naive approach is data parallelism, where you just divide the data you're training on. If you have, cat images or dog images, you assign different images to different GPUs and they train on them in parallel. And then you do some synchronization at the end to synchronize the network. The more complicated methods are where you take the neural network and divide that across GPUs and then compute in parallel. But once you divide a neural network, if you're trying to train the network, then you have to do communications across the GPUs to be able to synchronize across all the machines. So intra-layer parallelism is one example where you take individual layers of your deep neural network and parallelize them. Interlayer is where you take one layer or multiple layers and assign them to different GPUs. So my group works on a framework called Axon, which is a form of hybrid parallelism where you combine either 2 or 3 different kinds of parallelism. You either do data plus intralayer or data plus interlayer and combine that to get more parallelism. There are some frameworks that are popular. So NVIDIA has a Megatron framework. Microsoft has a DeepSpeed framework that people use for training in parallel. The framework we have been developing is called Axon. There's a link in the at the bottom. A message-driven parallel framework for extreme scale deep learning. So I'll quickly talk about what Axon does and show some performance plots. So it does a 2D, in one mode, Axon does a 2D hybrid parallelism. Let's see if this animation works. So you have a data set, a single batch of a data set. You break that into smaller parts. You divide that data into 3 different parts if you have 3 GPUs, and you let each GPU handle a portion of the data. So that's the data parallelism part. But if you also have multiple layers in the network, let's say you have 4 layers, you can assign 2 layers to 2 GPUs and 2 other layers to 2 GPUs. And so you can get a hybrid of interlayer plus data parallelism. Right? And then if you're doing data parallelism, you also have to synchronize in the end. So you start with the interlayer phase. You do a forward pass and backward pass. This involves some point-to-point communication. And then at the end, you do a data parallel phase, which requires a all reduce. Okay, so this is just showing the same thing again and the communication happening. So what we have shown is that Axon can train much faster than existing networks. I'm going to show 2 performance plots. This first one is on NVIDIA A100 GPUs. These are top of the line GPUs right now. H100 is the latest GPU. The plot here, if you look at the left plot on the x-axis, it shows the number of GPUs we are training on. The y-axis is time. The green line is Axon, which is our framework. And you can see the green line scales much better than the other frameworks. DeepSpeed and Zero are not scaling as well. So, and lower time is better performance. So we are seeing that Axon gives the best performance. Similarly, if you look on a different system, this is on AMD MI250X GPUs. AMD has recently entered the GPU frenzy. So we also have AMD GPUs now. Again, you can see Axon is the blue line. It gives much better performance than Zero or DeepSpeed. So on the right side, there's the number of the throughput you can get on each system. So you can see that Axon gets better throughput than the other 2 frameworks. So this is about deep learning, or how do you use high performance computing for deep learning. Just 2 more slides on, like I talked about, you're using ChatGPT to do. People use ChatGPT to generate code. Have people been doing that? Okay. So generating sequential code is easy. You just say, can you write some code that prints hello world or write a matrix multiply, right? But generating parallel code is more difficult. So what we are looking at is, can you use deep learning models like GPT to generate parallel code? So this is our project on, I'm only talking about it at a very high level, but this is on how do you use language models to generate parallel code. For this, you have to start with existing models for sequential code, but then you need to fine tune them on additional data, which is, you take GitHub repos that have parallel code, you fine tune the model further so it understands how to write parallel code, and then you see if it works. Even now, even models like ChatGPT are not great at generating parallel code. So this is current research we are working on how can we make these models better so that they can generate efficient and correctly working parallel code. Okay, this is just an example of, the prompt you provide and what you expect, but usually it fails at generating the correct code in these cases. Okay, so I'm going to wind up here. I lead a research group in the CS department at University of Maryland. My group is called Parallel Software and Systems Group. We do a bunch of different things, not just AI or parallel AI. We work on parallel applications and runtimes, performance analysis and tools, data analytics, modeling, and also self-tuning parallel systems. And all of this feeds into different kinds of computational science and engineering application. This is my research group, and I can take questions. Any questions? No? Okay, I'm happy to stop here. Thank you.
Thank you, sir. May I invite Dr. Anant Kumar Jaiswal, Professor, Amity University, to present a memento to our esteemed speaker, Professor Dr. Abhinav Bhatle, University of Maryland, College Park, USA. With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the fraternity of Amity University, Uttar Pradesh, thanks all the guests and dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank you so much, guys. Anand, sir, group photo, group photo, group photo. यहाँ पे खिंचाएंगे. Thank you, bhai.